Good evening, y'all. Welcome back to another Sunday night. Hi, Michael. Good to see you again. Hey, Chris, how are ya? Another Sunday night here in the lab, here in Dexter's laboratory. uh, it's been a goofy week, y'all. It's been very strange. I don't know about y'all. This week seems to go by very fast, and somehow very slow. But yeah, as Mike said, today was beautiful in Chicago, like 75, 80 degrees, sunny. I mean, we had some stormy days the past couple days, and it was such a nice time to have like an actual nice day to enjoy. Has been really good. So yeah, so feeling good and excited about tonight. Brian's already without pants, or maybe has been without pants all day. This is not a pants judgment zone. That's not what we're about. Am I wearing pants? Unless we get tummy cam later in the night, we may never know. We might get tummy cam. I'm not sure exactly where we'll end up tonight. But before now, this can be my little secret. Am I wearing pants? Oh man. It's gonna be a little bit of a goofy night, y'all. It's also gonna be a fun night. As always, we'll wait like a few minutes for people to catch up and get on stream. But as a reminder, tonight's topic is write better code. write code good. Which is not, again, this is a judgment-free zone. The best code is the code that works. And everything else is style points. But the reason we might want to write better code is because style points really help out not only somebody else you might be trying to read your code, but also you in the future trying to read your own code or make updates or come back to a project that you started years ago. And now it's like, oh, somebody wants to borrow that IR candle controller, or here's a one for Brian. We have an Arduino running like a jiggling water ripple machine in our museum, for example. And the code clearly works. Like that exhibit is literally, there's an exhibit there's multiple exhibits now at the place where Brian and I both work that run on Arduinos, which is super cool. And they're working. I hope that our code is all clean enough that like when we come back to them in 10 years time, we can understand how they work. Lee Business, hi. Lee and Travis actually texted me in the last like half hour calling me out on a couple of little typos in the circuit diagram from last week. So I've corrected it in the slides tonight and on the website now. I apologize if anyone was tricked, and an extra credit if you caught that the power and ground rails were shorted together like Lee did, or Travis did, and Lee caught that the buttons were backwards. It's all fine. It's all good. But thank you for catching that. I saw multiple pictures this week of people working on their projects, on the build together circuitry that we proposed last week, and asking questions and looking for code and doing sort of the stock project, doing sort of add-ons to it. Like it was super cool to just like hear from people over the week, like, hey, here's my thing, or hey, here's what I have so far, but it's not working. What do you think might be going on? It was super fun. Just before we dive into that, which is sort of like the thing we're doing tonight, I am drinking a Scent with Lasers from Beguile Brewery, just down the street from us here, local to us here in Chicago. It's a juicy IPA, and it is maybe my favorite beer since we started doing this 10 weeks ago, which is wild. It's so juicy. It's so good. It's wild that it's the best beer, and it's wild that we've been doing this for 10 weeks. Like, the little teaser down at the bottom of the screen here that says Arduino number, I had to change the font size because now it's a 2-digit number. Totally wild. But how cool! Like, I'm thinking back to that very first night where, like, I saw, like, Chris Wick, Brian, Lee, like, this list of names has been here many of the Sunday nights I know since we started, and I don't know, it's cool to see you all back here on Sunday nights again, as we build stuff and try not to break stuff, and do or do not set things on fire. It's a little teaser for what's coming up later tonight. Chris and Michael and Kenneth and I actually got together on Zoom on Thursday night and worked on some respective microcontroller projects. And we got a little preview of working with Flame that evening, so that might make a reappearance tonight. I have explicit permission from Mary, from my wife, to have contained fire in the workshop, and my fire extinguisher is nearby and ready to go. So again, if this cuts out immediately, it's either that there's like a sudden storm, or I've set the place on fire and we'll just abandon ship at that point. But let's dive into it, yeah? Let's do a thing. So the place we left ourselves last week was this like new idea. We'll scooch a little closer there. This new idea for how we might talk about writing code and writing more good code, writing code that am more good. And specifically, I wanted us to also be thinking about the same hardware as a basis for thinking about this. So whether... Why are you not advancing? There we go. Whether you built this or not, hopefully this is like enough sort of like few enough pieces to be comprehensible and enough interesting pieces that we can do sort of a variety of interesting things with it as a basis for our code. And then also to be like a jumping off point for doing other interesting things, or like expanding on this project, or pulling a piece out of your toolbox that I don't have, that you might not have, or not everybody has, and doing something cool. So the setup, just as a reminder for those who are playing along at home with their, with their individual setups in front of them, or for those of you who aren't playing along at home and are just like, I think I'll absorb this one through osmosis, which is totally cool. The setup is 5 resistors. In my case, I did red, yellow, green, yellow, red in that order, just because I think we'll do a nice sort of effect in the middle there, but 5 assorted LEDs will be fine. 2 buttons, and we'll use them in that input pull-up mode that we know so well. So they're just a button connected between a digital pin and ground. Here, I can make that go away. And then a potentiometer with one side hooked to the power rail, one side hooked to the ground rail, and then one side hooked to an analog pin. In my case, it's A5, but as we'll see, like changing which pins things are hooked up to is not terribly hard in our code. So, the specific digital and analog pins that these things are hooked up to begin with are not terribly important, because you can always change it to match in your code. But these are the ones that mine are hooked up to. I also proposed that we use an assorted sensor of your choice. Something out of your toolbox, but what I realized is like getting an assorted, like a sensor that you pulled out of the ground or somewhere else to work might be a whole evening in itself. And I know there are people who are working on this like Thursday, Friday, some people working on it this afternoon. Like if we don't have a sensor hooked up already, it could be the whole evening getting that working. So I'm going to go back and forth between using a little analog fire sensor as like my sensor of choice, but we're also going to write the code in such a way that it's easy to swap in the potentiometer that you already have wired up as your stand-in sensor for tonight. And we'll see like how it's easy to sort of swap sensors in or out, light sensor, sound sensor, in that case. So if you just have the potentiometer wired up, you can play along with us tonight and do all of the demos with one little change in the code. And the fact that you can make that change with one little change in your code will be sort of a feature of the fact that we're going to write some good code together. Other things we're going to talk about tonight, we're going to talk just a little bit more formally about arrays. We've used them a bunch, I think going back to week like 3. Like we've been using them forever, but we haven't ever really like addressed that they are a topic we're talking about in and of themselves. So that'll be worth touching on just briefly. Delta time is a sort of programming pattern that we've touched on sort of by accident in the past 3 or 4 weeks. That was, I mean, I'm sure you're sick of me hearing it. That's the programming idea of, rather than using the delay function to sit around and spin our wheels, we're going to use this pattern where we set what time we were going to want to check on the baby, and then we're going to keep looking at the clock to see if it's that time, and when it is, we'll take some action, and then we'll update our notion of when the next time we should do something is, and we'll make that more formal in a little bit. And assuming we sort of get through all of the programming tasks that we might have tonight, we'll look at a simple way to implement a program or a piece of code or a circuit that does things in sort of multiple modes. Often our devices want to be, if we're thinking about a sensor device or a garage door opener or something like that, will be existing in 2 or 3 different states, right? A garage door opener I'm just making up, but let's say, most of the time your garage door motor machine that opens up your big garage roll door is going to spend a lot of this time in a mode where it's just listening for a signal from your little car clicker remote control. But when it receives that signal, it needs to be doing sort of an entirely separate thing for a little while, which is moving the motor, checking on its sensors to see if it's come to the end of its travel or not, looking at that little stupid sensor on the ground that tells you if there's like a kid walking through the door, and if it is, do something else. But once those are complete, then it can sort of just go back into waiting for a signal mode. And thinking about moving between 2 or 3 or more different states that your machine can exist in, your device, is kind of a useful thing. And it's really not a hard thing to do, but it's not something we touched on yet. So we'll look at how we build that into our code. Tonight is going to be kind of fun for me. The last time that we did like a coding evening, I think was week 6. And it consisted largely, we built that like dot matrix LED. I'll pull it out because I have it. we built that dot matrix LED display thing, and then we spent like 90 minutes talking about code. And really, I mean, I spent 90 minutes yammering about code at y'all, and I just thought it was not a terribly interesting... Oh no, my thing came off. Not my thing. Oh, it's in the bin now. Oh, there we go. That's that quality back of head content that I know you come to us on Sunday night for. Us? Like I say, it's going to be kind of a goofy night, and here's why. Rather than doing this project over again, which was, hey, here's some pre-written code that I'm just going to like step through and like yammer at y'all about, and like, oh, and here's what you do next, and here's what you do next, which I thought was like, there's a lot of good content there, but like that's really boring. We're going to write code together tonight, and I'm going to do it all live. I have like 3 or 4 bits of code to get us started and kind of a plan for where we might go. But a lot of this is going to be written as we go, and none of it terribly complicated. So if you're following along at home, hopefully you can be typing along with us and troubleshooting as we go. The flaw in this plan, of course, is that like if we get too far ahead and you don't have the code quite working right, it will be harder to play along as we go. So this might not be a perfect situation either. But we'll give it a shot. I think it'll be a fun exploration of like how to do code together on Sunday nights, if nothing else. So put that back in the big bin O project to save for later. And we'll kick some things off. Where did I want to start? Oh, we talked about the circuit a little bit. Oh, so this was like the first 3 steps of the build together section of this wiring project that I proposed. And this project, as we sort of conceptualized it, was a device that would be some kind of sensor responsive thing. It has a couple of red LEDs that maybe will tell us like level of the sensor is too high, level of the sensor is too low. We have some sort of yellow LEDs and a green right in the middle. It just sort of evokes to me like, you know, whatever we're sensing, whether that's volume, whether that's light level, whether that's fire proximity, is it right at the level where we want it to be? Is it slightly too high or too low, or very too high or too low? And so that's going to be kind of where we're going to proceed tonight. That's a pretty loose specification for what we're going to do. If we were going to, you know, make a device to... Oh, hello. If we were going to make a device... Where are we? Hello. We're going to make a device to really serve a purpose, we might want to be a little bit more specific about what it was needing to do, under what circumstances, and with what timing, and with what kind of power. But for our purposes, let's just get started building the darn thing. So these are sort of the first 3 steps I proposed. And some of you may have done these already. I've been seeing some pictures and some things that make me think that we've already built a little bit of this, which is great. And I have, of course, already built some of the circuitry on the circuit board, but we'll walk through it in just a sec here. But this is how, if I was going to start building this project, and I am, here's the steps I would think about. Install all the basic components and test. And for me, that usually, I swearly, I actually haven't sipped the actual beer yet. I'm just in a mood tonight, I guess. But let me sip this beer, and I'll tell you how good it is, because apparently that's how I drink beer on camera. That's so good. So we'll start by installing all of our basic hardware, and we're going to test it. And to test it, I actually usually think about breaking that down into a couple of different steps. I like to start with my outputs for a couple of reasons. One is they are often, though not always if you're building like a robot, the simplest part of the project, at least in terms of like the basic functionality, right? Often we're talking about a handful of LEDs, or an LCD display, or a couple servo motors, and maybe it's a quite a bit more complicated process than that. And of course, like the relationship between when the screen versus the motors versus that, like it could be a complicated coding process, but just to get things sort of basically working is usually relatively straightforward. And it leaves you with a bit of code that helps you later test whether your things are still working. So these are the couple of bits of code that I threw up on the website this week. The LED test example. Well, let's see. You have to help me remember to hide the little extra window here when I do these things. Just a little bit of code, and this is literally like when I'm getting my inputs working, I write pretty fast and sloppy code. One of the themes of tonight is going to be like, it's a write better code evening. You should probably do as I say and not as I do, because I often write really sloppy code when I'm just like slamming through things. One of the things that I don't do a lot, but is a real gift to yourself in the future, is comments. As we saw, you can do the double backslash will give you a single line comment. So this is a comment. And in the Arduino IDE, at least, if you do /*, that will, and do an enter sign, it will give you sort of this section of text here, which, as long as you keep hitting enter, will keep adding asterisk for you, and all of this in here is a comment. So if you have a lot to say in a particular place, doing this multi-line comment with / asterisk and then concluding with */ is a good way to do multi-line comments. Yeah. And in this case, the things that jump out to me that like I didn't comment, which is not great because I handed this all to you without a whole lot of explanation, is like, what are these various variables representing? So I know I have some LEDs, and if I had the hardware in front of me, I could probably guess what they are, but I might notate that these are in order red, yellow, green, yellow, and red, and maybe it's useful for me to note that first pin is lowest in value, let's say. Might be a useful note for me to leave to myself. So if I come back to this, if I came back to this code in a year, how would I start to understand what these values mean? I should also say I'm also, if I'm just trying to get things working, I will often end up just dumping hard pin numbers in here with like, there's 5 numbers in an array, but the numbers themselves don't tell you a whole lot about what's going on here. You can also define more specific things in variables and then wrap them in an array. And if it helps make things clearer, and here's what I mean. I might say int low red equals 9, int low yellow equals 10, int green equals 11, and so on. And then in this array of LEDs, I could say, instead of having a 9, 10, 11, I could say I'm in order going to have an array that has my low red pin, my low yellow pin, my green pin. I'm going to need, I guess, 2 more pins. Int high yellow equals 12, and int high red equals 13. And so now I have an array of my pins that are associated with my LEDs in order there, but it's also telling me a little bit about what the order of my pins in that array is, because I've sort of defined these pins as variables, and then I've dropped them into this array here. This might make it a little bit easier later if I had to start moving pins around. Like, let's say, and just making up an example, let's say I needed to use pin 9 to do something else, and it had to be pin 9 because, I don't know, maybe I'm plugging a shield into the top of my Arduino that uses pin 9 to do something. A lot of shield designers sort of make assumptions like, oh, I'll just use a digital pin, that's 9, that's 4. And so I might have to pick a different pin to do my coding with. And in this case, I was like, oh, I moved the wire that was attached to the lowest red pin. That's going to be now on 6. And this makes it just a little bit clearer where I have to change things. Like I say, I slammed in this example really fast, and you could certainly do the same. There's nothing wrong with doing that, but this is just like one way to make things a little bit cleaner. Chris says, isn't there a command that will tell you how many spots there are in the array instead of defining that number? Good question. Yeah. There is a way of measuring the length of your array. I'm just in the habit of defining it here right after my array, but the code for that, Chris, is, here, let me do this. Let's say I had a variable called num_LEDs, but I'm not going to initialize it yet up here. The code would be, and I'll see if I get it right the first time, num_LEDs equals, is it length? What's the keyword? Yeah. Length LEDs 0. Let's see. Length LEDs divided by length LEDs 0, I think is correct. I might have the keywording wrong. Length was not divided into, what is the, oh, is it size of? It's size of is what I was thinking of. Length has to do with strings. I will confess, I'm going back and forth between C and Python a lot these days, and I get their keywords confused a lot, so thank you for bearing with. This is great. Like, feel free to ask questions as much as you want tonight. Like I say, we're kind of freeform tonight, so ask questions. Travis asks, what is my philosophy behind using capital letters or not? I will admit it's not terribly consistent, but I will typically use capital letters for anything that is not going to change at any point in my code, and especially anything I'm thinking of or actually declaring as a constant. Especially I'm going to use it as this const keyword. Anything that's going to be associated with the physical arrangement of my setup, I'd like to put in capital letters. That's just a personal style thing, but that reminds me that, like, if at any point later on I see something like you know, high red equals 5, right? This, to me, visually, is a red flag, because I'm like, oh, I'm assigning to a capital letters thing. Is this really the variable I meant to use? Probably not. In fact, because I've defined it as a constant using this const keyword, it won't even let me do that assignment. It said, hey, I'm not going to treat that as a variable at all. That's just a name for a number that you gave me right up at the top. So that's not allowed. There are manuals of style with like various opinions on how things are named. My general convention is all capitalized for constants, and then I like to have my variables in camel case, which is with the first letter lowercase and then the successive letters of later words capitalized. So like if I had a variable called LEDs in a row, I would capitalize each successive first letter. That's not particularly like anyone's style but my own, but that's just what I do. It doesn't matter to the program itself at all. None of the names of the variables themselves make it into the Arduino. They're all sort of replaced symbolically before they go inside of the brain itself. So it doesn't matter how long these are, but that's a bit of my style. Let's see. Guess a red LED, not a flag. Yeah. At some point tonight, I'm gonna say LED diode. I'm gonna say LCD display. I'm gonna have a lot of wordos in the evening tonight, I think. Where were we? Oh, arrays. We were talking a little bit about, I think, and getting our outputs working first. So this LED test code was the first bit of code that I threw up on the website before we looked at things this evening. And really all it is like, hey, here's a list of the pins that my LEDs are attached to. I'm going to do this for loop through all of them. I'm going to set them all to be an output, and I'm going to set them all low. I'm going to turn them all off. And then I wrote a little for loop that turns a single pin on high, waits a second, then turns it off and concedes. We're just going to step through each of our LEDs in turn and make sure they work. And you can see that's exactly where we are. This is actually the code that I'm running on this right now. So it's importantly, like, this is a really useful bit of code to write at the beginning of your process. I'm also like, I'm not going to get rid of this piece of code just because I've moved on to other things. I cannot tell you, and Chris and Mike can tell you from our adventures on Thursday night, I go back to code like this continually throughout the coding process. In fact, probably the most loaded sketch that I use is the blink sketch in the basics examples, which is literally just like blink a pin on and off. Because there are so many times, and I've heard this from a couple people recently, it's like, I'm trying to get the code work, but I'm not confident that the hardware is working, so I have a hard time telling whether it's the code that's the problem or the wiring is a problem, and that really kind of throws me off. And so, now I have this bit of code that I know will cycle through my LEDs one at a time, and so if I'm ever concerned, like, let's say I get to a point later where, like, red, yellow, green, yellow are working, but red on top is never turning on. And we've gotten some mess of code about sensors and thresholds and all this stuff, and I'm not sure. Probably what I would do is just load up this test code against it and say, hey, does this still work? And if this LED doesn't turn on running the test code, it's like, oh, great, wiring problem. Strip it down to its most basic components. I got a wiring problem. Let's fix that and come back to doing code later. So holding on to your sort of unit test code is really useful. Unit testing is a concept really on the software side of things that refers to testing the smallest possible units of a problem individually before you assemble them into a whole. And this is my way of thinking about hardware unit testing. Right, this bit of code is only testing these LEDs and nothing else. It doesn't even know that there's buttons and a potentiometer and a flame sensor hooked up. Doesn't care. And so that's going to be useful to us now because we know it's set up, and later if we run into problems, which we might tonight or in general. So we shall see. So that's my first tip of the evening. Get your outputs working first and test them in isolation and hold on to that code. It's always good to be able to go back and say, hey, I've been futzing with this thing and writing a bunch of code and shoving it around the desk. Is the hardware itself still working? Yeah? So that's my first tip. We talked a little bit about arrays just a moment ago, and I'll be jumping all over the place tonight, but I don't think that's terribly different from any other Sunday night. But an array, like we have our array of pins that are now holding the values of the pins that our LEDs are attached to. An array in C, in Arduino language, is just a list. It's a list in order that contains a certain number of variables, all of the same type. And that's pretty much reflected in the way that you declare it, right? If we look at our list of integers here, that are the pins that the Arduino is attached to, I'm declaring it actually as an integer list, right? All of it's going to say about a bunch of integers. The list is going to be called LEDs, and I'm going to put a number in here later to tell you that I want to look at the 0th or 1st or 2nd or 3rd or so on member of that list. Which is only to say, we have only been working with lists that have a single type of variable in them, because that's the only type of lists generally that there are in C. You wouldn't see an array that had, I don't even know how to type this, array that doesn't work, we'll call this. You can't put apostrophes in there as well. But I couldn't say array is for, cheese, false, print. Right? There's lots of things wrong with this, but the one that I want to point out is that there are different types of variables in here, and I actually wouldn't know how to declare this as an array, right? It's not an array of ints or booleans, like that true-false value, or strings, like cheese. An array in C can only be an array of one type of things, generally. If we have a reason to need to index multiple types of data, we'd have to be quite a bit clever about it. Like if for some reason your program needs you to know that the first member of this list is for, the second member is cheese, the third member is false, I'm not quite sure what you're listing here, to be honest. But to be fair, like, let's say this was a list of user-generated names or user-provided names, you might actually have a list that is in quotes for and cheese and the word false and the word print. Like you could have an array of strings and this would be fine. This though would not be a number. This is sort of the digit 4, like you would take out of your printer's box and stamp on paper, and it doesn't represent the number 4 in its current form. That's sort of the closest we would get to like representing multiple types of data in a single array. Like I say, I'm not quite sure when you would run into a need to do that in a more explicit way, but I thought it's worth calling out. Arrays are of one type of variables. And as we talked about a moment ago, they can be instantiated from other variables. This is that example I was sort of getting into with, rather than making this this LEDs array where our LEDs are hooked up be 9, 10, 11, 12, we can give our other give those variables more suggestive names and then build the array out of them. It's up to you, really, whether this or the previous example, which is, int LEDs equals 9, 10, 11, 12, 13. Is that more readable than this? I don't know. This is certainly more concise. And for a little bit of test code that I was writing for myself, certainly you saw what I posted online. This is what I wrote. This is certainly more communicative, but it's also sort of an additional mental burden on whoever's reading the code to figure out what's going on, which might be really useful. Like this instantly tells me, the lowest LED that is red should be attached to pin 9, whereas this sort of makes me work for it. But a lot of these choices are like about concision versus being expository, right? This tells me more, but takes more brain work. This is more concise and easier to take in all in one go, but it doesn't tell me as much. And that'll be a choice that I think we keep coming back to in all of these things. Oh, Kenneth points out, if you're using pointers, which is beyond our scope tonight, you can have collections of different things in C, but that is beyond our scope, but beyond a simple C array, let us say. But a fair point if you're getting deeper down the rabbit hole in C, and I encourage you to. So that's I think all that we really were going to talk about arrays for the beginning of the night. I just wanted to call out a few points that we hadn't touched on. I guess one sort of in the middle here is that an array in C at its base has a set length when you instantiate it. So when, for example, I said that this LED array is going to consist of these 5 members, that means that this array can and will only ever be, until we reinstantiate it, only have 5 members in it. I could change their values. I could say, so let's say in my setup function, I could say LEDs 0 equals 6, and then our 0th position of our list here, because remember, arrays count from 0. Our 0th position of our list here would be 6, so this would be then 6, 9, 10, 11, and so on. But I couldn't do LEDs, so if our positions are 0, 1, 2, 3, and 4 for our 5 members array, I can't do LEDs 6 equals something, because our array is only of size 5. It's going to throw up on me a little bit here because I've defined this array twice. It will let me compile, but this value here, this 6th value, is technically undefined. It's outside the bounds of our array. So we're writing to some point in the Arduino's memory that it has no idea about. It doesn't even know it exists. So just be aware of that as you're defining your array sizes. You are defining them once. You're defining them once and for all. As Ken points out, you can do this, and it does compile. You just shouldn't. And to make a little bit more clear why that is, when you declare an array like this, I wish I had a good graphic set up for this. When you declare an array, this is basically telling the Arduino to say, hey, set aside a little sequential chunk of memory that's able to hold multiple sort of variables in a row, and remember where the start of it is. And I'm going to tell you what kind of information I'm going to store there, so we know how many literal bits, how many ones or zeros, or how many bytes, chunks of 8 bits, how much information, how much space I'm going to need to set aside for this array. So in this specific example, an int takes 2 bytes, takes 16 bits, so I'm going to store 16 plus 16 plus 16. I'm going to set aside 80 bits of information in a place. I'm going to remember that place is going to start at a name. I'm going to give that the name LEDs. And then when I ask it to give me that information back, it says, okay, well, I remember I started at this location in memory. I know that each position takes 16 bits. I'll just do a little multiplication by the position they asked for, and I'll jump ahead, by 16 bits and 16 bits and 16 bits. And I know that those next 16 bits are a position in this array that our programmer is asking for. Hullabaloo. Now, what happens if you put a number outside the bounds of your array? It'll do the exact same thing. It'll say, hey, I know where the chunk in memory that this list starts. I'm just going to jump ahead by 6 times 16 bits and just get there and return what's in memory there. The only thing is, we haven't defined any information going out that far, and so it might be related to something else. This is going to be gobbledygook. It's going to be whatever happens to be in memory. It could be some other variable is living in that spot. So overflowing the end of the bounds of your array, this is an array overflow error, or a buffer overflow error, leads to unanticipated results. So it won't throw up an error for you, but make sure that you're staying within the bounds of your array, or bad things can happen. That's kind of a tangent, and it's really all Kenneth's fault, so I wouldn't worry about it. All right, so I think that's probably all that we have to talk on arrays for the moment. My next tip, so once we have our outputs working, let's get our inputs working. And again, good to test it in isolation. I threw up some code on the website that's actually a little bit more involved than I normally would do. Here's sort of a basic example of how I like to test my inputs in a simple case like this. I declare some variables, so in my case I have my knob, I have my potentiometer hooked up to A5, but my first button's on pin 7, my second button's on pin 8, and I like to just, set them all as input pull-up, and then spit out some information to the serial console that just tells us whether they're being pushed or not. So here's a little bit of code. I'm just going to, in this loop, I'm going to take an analog reading of the knob, print the state of the button, print the state of the other button, and then wait, in my case, a quarter of a second, because I kind of want to be able to see whether the knob is doing anything when it is spinning. So let's upload this, and we'll do just a quick little demo. The bit of code that I put on the website is a little bit more involved than this, and we'll look at that one in a second because it'll be a good jumping off point. But now I can sort of see I can twiddle the knob, that's changing. If I push one button, that's changing. I push the other button, that's changing. Good. Everything basically works. And I'm going to hold on to this bit of code too, because again, if I'm ever concerned, and I am a little bit concerned about how wiggly these buttons are on the breadboard, I can always come back to my basic unit test, my basic fundamental test bit of code it doesn't know about the LEDs or care, doesn't know anything else except it shows me the state of the button. So if I'm ever thinking I have a hardware problem, I have a test that's related to just the hardware. Trying to debug a software problem and a hardware problem at the same time sucks. So try not to do it. If you suspect you have a hardware problem, go back to your unit tests, test things in isolation, and if you're confident that the hardware is performing like you think it should, then you can go back and start figuring out what's going on in your code. So I highly recommend getting your inputs working before anything else. Oops, there we go. we'll do that. And again, hold on to that code, save it somewhere, call it input test. Part of the thing will be like if you're working on a final bit of code, you might move some wires around. You might have to redefine those constants at the top that told us where things are plugged in. And that's fine. Like that's an 8-line bit of code, right? That one I'm not going to worry too much about commenting the hell out of it because it's simple enough that I'm going to be able to, figure out what's going on, especially if it's you or me or yourself coming back to your code to troubleshoot it a little bit. All right, let's talk about delay. Delay, and I think you are all familiar with this by now. Delay, super useful, super tricky function. Delay says to your program to pause for a number of milliseconds equal to the number that you give the function. So, just to make that explicit, I think you have all seen this by now, this delay statement here, delay 250, says, hey, sit and spin your wheels for 250 milliseconds before you move on to whatever the next line of code is. So that is a really easy and fast way to write a piece of test code like this one. Like I want to do a thing every quarter of a second. I'll just like do it and then I'll say, hey, sit and spin your wheels for a quarter of a second, and then I'll do it again and again. So it makes things writing code like that, or honestly writing code like our LED loop that we're using as our unit test here, really easy, really fast, pretty predictable, really great. Here's the problem though. It brings everything to a grinding halt. The best analogy, as I've been trying to come up with one for what the delay function is, using the delay function in a piece of code is kind of like, if we're building a car like we're building a program, using the delay function is kind of like pulling the car off to the side of the road, stopping and putting it in park before you do anything else. So let's say that we were testing our headlights, which is kind of the, the analog of getting our LEDs working, right? We just want to make sure some light comes out of them, right? If all you want to test is, hey, are my headlights on? Then yeah, pulling over to the side of the road, stopping, putting it in park, and then turning the headlights on and off is actually probably the easiest and fastest and most reliable way to do it. That's fine. But if what you want to test is, are there adverse effects if I step on the gas while changing lanes? That's a perfectly reasonable question to ask about a car that you're building. But there's really no way to test that in a manner that involves you pulling over to the side of the road and stopping and putting it in park. In fact, some of those things are directly antithetical to this idea of stepping on the gas and changing lanes, especially if we're doing them at the same time, right? So using the delay function is it really does grind things to a halt, which sometimes is what we want because we want a sort of a clear picture of doing only one thing at once. But if the goal of your program is to do multiple things at once, delay is to be avoided if you can at all help it. And by do multiple things at once, I'm lumping into that category both doing things as output and looking for things as input. And for a lot of categories of what we're going to do and what we're going to do tonight, we might only be doing one thing as an output. We might be saying, oh, only one LED is going to be on at once. But I also want to be looking at the input at all possible times. And so in that universe, we want to try and write the delays out of our code once we have it working in a basic way. And this is not shade at all. I will usually write a quick bit of code with delay, get it working. Hey, the LEDs work. Hey, the buttons work. All right, now how can I sort of morph this code in a way that takes that delay out of the picture so that we can do more things at once. And the way that I usually do it is this pattern that we've we've given a couple different names over the weeks. This is like the watch the baby pattern, that sort of name that sort of sprung out of nowhere a few weeks ago. But the watch the clock pattern, we might call it a little bit better. You sometimes hear this called like the delta time pattern, which is a slightly different thing. Which is a way of here it is in simple terms, in case you need a refresher from the past couple weeks, right? Let's say I'm gonna pull let's say we're baking a cake, and I know that I'm baking cupcakes. I'm gonna bake 3 batches of cupcakes, and I know they each need to be in the oven for 20 minutes. How would you deal with those 20 minutes when you bake a cupcake? Would you pour the batter in the first tins, put them in the oven, close the door, and then literally sit on your hands and do nothing while counting to 1800 seconds? Or would you put the batter in the oven and then continually check the clock and say, hey, when it's 20 minutes past when I put those cupcakes in the oven, I should take them out of the oven. You take the first batch out, you put the next batch in, and you look at the clock again and say, oh, now it's 4:37. When it's 4:57, I need to get those cupcakes out. Now, you do have to still keep an eye on the clock, right? The clock isn't kind of come over and like drag you back to the oven itself, to sort of torture the metaphor a little bit. But you know, that way of thinking about things, right? You're just going to be constantly checking the clock, like, hey, is it time for that next thing to happen? Is it time to pull the cupcakes out? And whenever I pull the cupcakes out, I got another batch to go in, so I can't go right back to sitting down. I have a few things to do each time I check that clock. But that's going to be a lot more productive for you in your baking life, and a lot more productive for our code than literally sitting on your hands, which is what the delay function is. Have I beat this metaphor to death enough? I honestly, you know, this is one of those things where, candidly, I feel like there's a lot of metaphors that we come up with in these Sunday nights and in this programming. And I feel like maybe if I throw enough of them out there, this is my experience is, you know, some metaphors really click and some metaphors don't, even if they're explaining the same thing. So hopefully something clicks, something gets into your head. Maybe it's that one. Maybe it's the idea of like constantly looking at that stovetop clock to know, is it the next time that I'm supposed to swap the cupcake trays? Just another thing to think about. So in code, here is the gist of the transition from a structure that involves delay to a structure that involves this watch the clock pattern. I apologize for the kind of tortured formatting of this slide. I really wanted these two to be on the same screen, and with the way that this is all laid out, it got a little bit compressed. But in the red here is a really common programming structure. In fact, it's the code that we've got running right now to make our LEDs flash and test our input. In this loop function, we do something, we do some stuff, we turn some pins on and off, we send some serial commands, and then we delay for some certain amount of time, right? Really easy thing that happens every some number of milliseconds. In the green here is the equivalent in our watch the clock pattern. And you see, it is a little bit lengthier, but the advantages are that we don't grind to a halt when running it. So it takes two variables. To do this, you need to remember the last time stuff happened, right? The last time I put the cupcakes in the oven or something like that, you'll want this to be a long integer. We talked about this a few weeks ago, but the reason for it being a long integer is that it can just hold more numbers than a standard integer. It's a 32-bit number. And so you can count to a higher number of milliseconds before you sort of run out of space in that number and reset to 0. So when you're working with time, and with milliseconds especially, just use a long. It'll make your life better. I typically also make my interval a long integer. This could be a regular integer, because a regular integer can count up to like 32,000, I think, or if it's unsigned, 63. I might be wrong. Oh, no, 32,000 if it's unsigned, 16 if it's signed, or minus 16,000. I don't know. Kenneth will tell you in the chat. Use a long integer so you can count to billions and billions, and that will be much more helpful to you. So the structure is, you know, to remember the last time you put the cupcakes in the oven, and how long the cupcakes are supposed to be in the oven for, in our metaphor, this interval. And then within your loop function, you'll say if millis, remember the number of milliseconds since we started, if millis is greater than the time the last stuff happened plus interval, so right, if the current time is the time the cupcakes went in the oven plus how long cupcakes bake for, we need to update our mental note of like what time it is, like what is the time now, and then we do some stuff. We take the cupcakes out, we put the cupcakes in, we stir the batter up, we hollow out to your friend that there's frosting that needs to go on, or whatever you have to do. But this is the sort of general pattern of the watch the clock pattern, we might call it, you set up your clock, you set up your interval, and every time you're past that interval, you remember the new time, and then you do some things. So let's take a bit of code that we've already written that uses a delay, and let's rewrite it together to use this watch the clock pattern. So let's see, let's do, what's a good bit of code here? Maybe our LED test code? What is our LED for loop code doing? Let's see. Oh, here's a good bit of code. So this is very similar to what's on the website. It's actually pared down a little bit as sort of a simpler place to start. So this is code. It's going to take in we've got our 5 LED pins. We have our knob and buttons hooked up. This is irrelevant for now. I'm going to define my LED pins as outputs and turn them off. I'm going to declare my inputs. None of this should be terribly a surprise. And then here's the place where I'm going to start, and I'm going to rewrite this code together. So this is a very simple LED test bit of code. It says, for I equals 0 to the number of LEDs, so for each LED in turn it on, read the analog pin and delay a number of milliseconds that's proportional to the analog reading, and then turn it off. Right? So if I upload this code, and if you're running the other set of sample code from the website, this will function very similar, just without that sort of reversing function. As I dial my potentiometer up and down, we'll see as I dial the potentiometer up, it rolls faster and slower. If you're running the second bit of test code on the website, this is exactly what it's doing. I'm actually going to basically recreate that bit of code and show you why it's written the way it is. Don't wait 2 months for an LED turn on. Yeah, not a bad idea. So let's rewrite this bit of code into our watch the clock pattern. So the first two things I know I'm going to need are a couple of new variables. I'm going to say long, I call it prev time, previous time. Let's just call it previous time, that something happened, and that will start at 0 milliseconds. And I'll say my long interval. For now, my interval will be, let's say it starts at ½ a second, and we'll see it won't actually matter that much what my initial value is. So I've got my two variables to hold my information. That's great. So my doing stuff in here is going to be turning some things on and turning some things off. And this actually highlights another challenge of the watch the clock pattern, is I'm not really going to be able to use this for loop to manage which of the LEDs is on anymore, right? I'm going to want to sort of be able to manage for myself which LED is turning on each time I hit that new point of taking the cupcakes out of the oven. So let's set up one more variable that is int LED. Let's say I have a num LEDs variable already. So let's call this current LED, and we'll start that at 0. All right. So let's do this. So first we'll create our little wrapper, which is always of a standard form, which is if millis is greater than previous time plus interval, I called it, then previous time equals millis, and then we can do some stuff. Great. So that's a very simple bit of structure. So like now we know that whatever we're going to do that affects the LEDs, we'll do it inside of this if block, because that's the only time we should be sort of doing this action. So let's see. So what I want to do, I want to light the next LED up. I want to turn the previous LED off. So when it's time, we'll turn off, we'll digital write LEDs, current LED number. So the current value of the LED I want to turn off. We'll write that low. I'm going to say current LED equals current LED plus plus. Or +1. They are the same thing. We'll add 1 to that variable. But I'm also going to want to make sure, right, this is going to go between 0, 1, 2, 3, 4. And when it gets there, I want to wrap back around to 0. 0, 1, 2, 3, 4, 0, 1, 2, 3, 4. So for that, I'm going to use this modulo operator. I'm going to wrap all these in parentheses and do this modulo, which is the percentage sign. Modulo the number of LEDs. So that's, remember that modulo is the remainder when we divide the first number by the second number. So if this value is 0 modulo 5 is 0, 1 modulo 5 is 0, yada, yada, yada. When I get up to 5 modulo 5, well, 5 divided by 5 comes out nice and evenly, so its remainder is 0. It's going to have this nice wraparound value that we want. Using this modulo operator when we're replacing for loops, really useful, right? So I'm going to increase my LED index by 1. I'm going to wrap back around to 0 if it's too high. And I'm going to write my new pin, LEDs, current LED, which is now our higher value, is now going to be turned on. And I think that, so that is going to, this is now going to pause for an amount of time equal to interval. Remember, I haven't integrated this analog read section yet, but let's just comment this out for now. And we'll see if this runs at a ½ second time step before we get too far. Kenneth makes a good point in that the actions that we're taking within this if-then statement inside of this loop are actually, we're not waiting exactly 500 milliseconds. We're waiting 500 milliseconds plus the time it takes us to execute our little snippets of code. So this is not a great way, I would say, of like making a clock. If you really care about the accuracy of specific time, you shouldn't be, allowing your code to eat up little bits of that time by running to keep track of it. You'd want to keep track of that time in another way. But for things that happen about once a second or about every 500 seconds, this is usually a decent enough approximation. Let's call it an artistic 500 milliseconds. So we can see, having uploaded that code, we're now advancing through our LEDs every half a second, every 500 milliseconds, like we thought we would, which is a very good sign. So now let's integrate in our analog read. So we have a couple of different things we could do here. One would be that we could put the analog read, so analog read, what did I call it, knob pin? I'll just copy and paste. Copy and paste is great. Let's say analog read knob pin. I could say that our interval is equal to our analog reading of our knob pin each time that we update our LEDs, right? So each time I take the cupcakes out of the oven, each time it's time for the next LED to turn on, I take a peek at that knob, I say, where is it set? I'm going to update my interval based on that. So that will work, and that actually might be a choice that you're making in the way that your code operates, is you're only updating your timing when your LEDs change. The consequence of that is, let's say I turn this all the way up to a maximum value on our analog reading, which is 1023. That means that if I turn it all the way up, we should be, you know what I will also have to do is say interval equals, no, that's right, is when this is turned all the way up, it's going to take me about a second for things to advance. If I advance this knob all the way down in between those readings, I still have to wait that entire interval of a full second before things start to move again. I'll show you that again. So if you watch, these are going to tick ahead about once a second. And I'm going to see if I can, right when one turns on, I'm going to crank it. But you see, I still have to wait that full second because we're not updating that value until we hit that next point of update. So one thing I could do is actually move this interval value outside of my if-then loop. So this interval is always going to be equal to the value, always, millions of times a second, going to be equal to the analog reading on my knob pin. So if I change its value in between updates, in between steps of this loop here, I will still, if I were to shorten this by a considerable amount, even between LED updates, I'm instantaneously going to see results. Does that sort of make sense? I'll show you on the table. Let me know if it does. So it still should have the same effect, right? If I turn it all the way up, to my highest possible value of my analog sensor, that's 1023 milliseconds. If I turn it all the way down, it gets very, very fast. But as I vary them in between, I should be able to, I guess we'll find out if I'm right, if I alter this just when an LED changes and I crank it, I see an immediate result because I'm not waiting for that next time step to update my analog reading. Does that sort of make sense? It's kind of a tangent. But thinking about where you're looking for, so this is an example of I'm taking actions on the outputs at sort of a regular time step, but I'm constantly looking at the inputs because they may affect when that next time step is. And by constantly, I really just mean every time that I move through this loop. And that's, I guess, kind of the takeaway of this watch the clock pattern, is your goal is to be moving through this loop function over and over and over and over again, because the faster you move through this loop function, the sooner after you pass that, that clock time when it's time to take the cupcakes out, the sooner you're going to see it. If we put any kind of delay, if we put a bunch of math in here that has to step through thousands and thousands of things, this will still trigger, right? It will still pass the time when the cupcakes are going to come out, but if we're so wrapped up in some other bit of code that we're too busy to move on and have this, get to this point in our code, then it doesn't really do us any good. So when you're using this pattern, you kind of want to be moving with some speed through your loop function. You want to be sort of checking this as often as you can. Doing a single analog read out here doesn't really matter. Doing 100 analog reads out here probably wouldn't matter. You wouldn't want to do thousands of analog reads, and you wouldn't want to delay if you can avoid it. That sort of makes sense? Questions, comments, issues, concerns? I know Kenneth's been answering some good ones in the chat here. Let's see. If you really care about things that happen every interval, and not every interval plus EV milliseconds, you want to say previous time equals previous time plus interval. Yes, so you can choose to update your previous time directly from the milliseconds counter or from the time step that you're expecting to see. But for a lot of our purposes that things are happening in human time, it's not, I guess Ken says, not going to make a ton of difference. Right? That is the gist of the watch the clock pattern. So we add two more variables, we wrap everything in this if millis is greater than the last time stuff happened plus the interval pattern, and that will sort of give us this same structure, but instead of using delay, we're going to be free to do other things. Cool? All right. Little wordy, but I think worthwhile of a thing to talk about. So let's real quick, let's talk about sensors. Because I realize that's the one part of this project that you at home may or may not be participating in tonight. Because I know sensor is a wildly big category of things, right? There are sensors that sense light, and sensors that sense flame, and sensors that sense heat. And the way that they communicate with an Arduino, there's dozens of ways that they could be doing it. The way that I'm going to be using for my sensor tonight is I have a sensor that outputs an analog voltage between 0 and 5 volts. And so I'm going to use an analog pin to directly read that voltage. In that sense, you can use a potentiometer to do exactly the same thing, right? Because it's going to, if you hook it up with one side to ground and one side to fire, you get an analog voltage out on the center pin. So all the things we're doing tonight, you can do with the potentiometer. But you could, because we're only going to be reading from our sensor in sort of a defined way in our code, it should be relatively easy to drop in a piece of a sensor that communicates in some other way. You just might have to be a little bit more specific about how you do it. Now, what do I mean by that? What happens if you have a motion sensor that gives you back in a digital way, a number between 0 and 10, where 0 is I see no motion and 10 is I see lots of motion. Will that still work with our code? Well, you might have to do some translation in code between, what does 0 from that motion sensor mean and what does 10 mean, and translate that somehow into, a number between 0 and 1024 to sort of be in the same range as this analog sensor. But this will essentially work the same way whether no matter what kind of sensor you end up using, but the sensor interaction code might be specific to your sensor. Let me do a better example. From ye olde big boxo sensors. There we go. You can see all the glare. My little fire sensor here outputs an analog voltage, but what else have we gotten here? If I was using something like, I have an IR avoidance sensor, which gives back some reflectivity of a modulated IR signal that comes back. So I would be getting back either the presence or absence of a digital signal multiple times a second. I have a joystick here, which really is just two potentiometers in one. So that would work as well. I have a digital temperature sensor in here somewhere. Oh yeah, I have a digital temperature sensor that would be giving me back digital commands. But all of these you can essentially make to work in a similar function, and I will show you where that fits into our code in right now. Not in just a second, in right now. So let's start turning our code that we've written into something that we can use to read our sensors. I'm going to build off of this code that I've written here that incorporates the watch the clock pattern that we've used. So remember, if you're working from the example code, we will need to have defined 3 more variables: previous time, interval, and current LED, up in our sort of setup area at the very top here. Not in our setup function, at the top of our code, I should have said. And then inside our loop, we're going to, for the moment, update our interval using an analog reading of that particular pin. And then we'll incorporate this watch the clock structure here. So if millis is greater than previous time plus interval, previous time equals millis, turn off the previous LED, step ourselves one higher, modulo the number of LEDs, and turn on the new LED. So if you're following along at home, that's the sum of the changes that we've done so far. So if I were to start to incorporate a new sensor into this, here's what I would do. The first thing I'm going to do is define a new function that's responsible for establishing what my current sensor reading is. I'm going to call it int read sensor. Let's get rid of that. And remember that this int here, this integer notation, means that this function, when we call it, is going to hand us back a value that is going to take the form of an integer. In the same way that when we use this analog read function here, it's giving us back a number, or this function that we're about to write is going to give us back a number, and in this case I'm saying, hey, it's going to give us back an integer. So I'm going to start by just saying, I'm going to say my read sensor is just going to return the value of an analog reading on my knob pin. And then I'm going to set my interval equal to the, let's see, what did I call that code? Read sensor. So I'm going to say interval equals read sensor, right? If I upload that code, it should do exactly the same thing as the previous code was doing. We sort of just moved that analog reading inside this read sensor function. This is a really common suggestion that I have. It's probably in a slide later, but slides take time to get to. When you're adding new functionality to your code, like we're going to do now, we're going to sort of broaden our ability to read other sensors. I always suggest expand your possibilities by doing the exact same thing first. So when we wrote this code just here, right? So I'm going to add a read sensor function, and I'm going to use it to inform what its interval is. But the first thing I'm going to do is have it replicate exactly what it was doing before. And this is a really easy check that I haven't screwed something up in how I've written the word read sensor or where I've put it in my code. You know, I'm doing exactly the same thing in just a slightly fancier way. When we get to modes later, right, if we're going to act in 2 or 3 different modes, you might first start by writing in the code to handle switching modes, and then only have one mode, which is what you already have, right? It's good to work in these little steps where you replicate what you already have by writing it in a more flexible, a more expansive way. It's kind of what we did the very first thing, right? We took that for loop with delay and we rewrote it in terms of millis and this watch the clock pattern. It didn't accomplish anything really new for us, except it's going to open up new possibilities next. But because it's giving us the exact same results, we can sort of quickly verify that, like, yes, we wrote the code correctly. So we know our code is working how it should be, if that sort of makes sense. So inside this read sensor function, this is the place where I'm going to handle my sensor, whatever it's going to be. And in fact, I'm going to do a nice thing for myself later and say this is going to return a value between 0 and 1023 to reflect the current sensor reading. So now, if I get to a sensor later that only has maybe 12 possible states, I haven't seen Palmer with a snipe who I know had like a water level sensor. That water level sensor might only return like 24 possible values. So I'm going to declare for myself that this function will be responsible for returning a value between 0 and 1023, no matter what's happening on the back end. And that basically guarantees that any code that's relying on it can assume that the value from this read sensor function will be, at the lowest 0 and the highest 1023. Ways you might handle a sensor that only outputs 24 possible values. Good candidates include the map function, which you may recall. Let's say, let's do I'm going to make up a little bit of code here, but let's say we had a sensor that only gave us values from 0 to 100 on our analog pin, as opposed to 0 to 1023 native. I could say return map analog read of whatever that sensor pin was, which normally is from 0 to 100, but I want you to scale it up to 0 to 1023 for me. The map pin is really useful if you have things that are appearing in a constrained range and you want them to appear over your full range. And we'll do this with the fire sensor in just a second here. But I'm just going to declare that no matter what happens, this function is going to be responsible for returning a scaled value between 0 and 1023. And this kind of comment is really common in well-written code, because the goal is to write good code. As part of the function declaration, to tell us what kind of value is it returning, what does it represent, and if you have any variables associated with it, if you have any variables in here, it's really good practice to say that those variables are the pins to be affected, or maybe they represent a motor or what have you, just as like a little priming for, hey, what is this function giving back and what is it taking in to do its job? So good practice is to sort of comment your individual functions with what they should do, what they should return, and what variables they take in. So for my example here, I'm just going to start by do an analog read on the pin of my knob, and I'll re-upload that. And we should see works exactly the same as before, which is great. That's great. So the nice thing about sort of encapsulating this into that sensor read function is now I can change the behavior of my code by only changing what's happening within that read sensor function. Like, for example, I have my fire sensor here hooked up to, what is it, digital pin A0. So if, in my read sensor function, if I'm going to change this, I'm going to say read analog pin A0 instead. And thankfully, oops. Oh, I shouldn't have a variables variable. That's just going to confuse things. I have a candle here that we'll make a little fire with. There we go. Ugh. Yeah, Chris says baby steps to the code so you know what's wrong instead of guessing 20 possible things. Yeah, it's always good to work from a place of knowing what you have and incrementing slowly through changes so you can tell what has changed and what hasn't. So let's see here. So in theory, what is happening here is this analog sensor is returning a voltage between 0 and 5 volts based on how much I think infrared light it sees at this infrared diode. And that's going to be influencing the behavior of our LEDs just like our potentiometer just was. So if I block the fire from it, we should see that it's progressing fairly slowly at about 1 second. But if I hold it up to the fire, it should move quicker. Yeah, interesting. It's a fire-scented candle. I'll tell you a story from the other night. We played a little bit with this candle on Thursday night when me and Chris and Mike and Kenneth got together, and I uncapped it. I lit the candle and I turned away to do something else, and then I had a moment of panic because I smelled smoke. Something on the workbench is smoking. That's never a good smell. Yeah, it was the candle. I was an idiot. So hopefully I won't have a similar panic attack tonight because, it's fairly obvious what's on fire here on the workbench this evening. So here's a point where we get to start making choices about our code and what it's doing. So just based on observing these LEDs, let me come back to the table here. Just based on observing these LEDs, right, we know that the minimum possible value is 1,000, the maximum possible value is 1,023. That's going to be about a second of wait here. The minimum possible value should be essentially cycling through these LEDs almost instantaneously. But you can see even when I point this right at the fire, we're not really getting close to that maximum possible sort of increment value. So do I want to sort of scale my input from the sensor when it takes the reading, or do I want to do it somewhere else in code? Let me show you what I mean by that. So here in this read sensor function, I'm just saying returns a value between 0 and 1023 to reflect the current sensor reading. If I suspect that my maximum reading and minimum reading are not 0 and 1023, do I want to put a map function in here that says, this is maybe 200 to 800 and stretch them out to the full range? Is this the right place to do that mapping? Or should I be doing that mapping somewhere up in my main loop? Or should I be writing a new function, maybe a function called map sensor reading? Call it, let's call it get scaled sensor reading. That would return a mapped value of our read sensor function. Right? I could chain these functions together to sort of do that. Which of these is the correct answer? And the truth is there is no correct answer. I could put this mapping here. I could put this mapping here at my read sensor function. I could put the mapping in my current section of code. So how do you know which of these to do? Well, it sort of depends on your situation. And I'll tell you how I would start thinking about this, right? So I've said that this read sensor function is going to return a value between 0 and 1023, and as a thing that just reads a sensor, that seems like a pretty reasonable thing to do. So I'm going to leave this read sensor function as a raw reading of the analog value of my sensor. But I'm also going to make use of a sensor scaling function as a separate function to allow me not only to sort of map that analog value to a wider range, but also this scaled value, this might not be, maybe I decide later that a linear mapping isn't perfect. Maybe I need to be extra sensitive at the bottom range and less sensitive in the middle and more sensitive at the top. Like maybe just one map function doesn't do it. Maybe I have to do more math in here. So having this broken out into its own function feels like the right thing to be. It might also be making things more complicated than it needs to be. But for now, that's where I'm going to go. So I'm going to say let's see, what did I call it? Get scaled sensor reading. Right, so again, I really haven't done much else differently here. I've introduced this map function in between our analog read and our sort of interval. So things should look a little bit different. Yeah, Travis, you're way ahead of me. So I'm going to use useprint to see the actual values. Yes, that's a great idea. So we'll go back to Travis is suggesting a really useful thing for how do I know what those actual analog values are that I'm playing with? Well, I have this test input bit of code that we wrote earlier that's going to print that analog value to the serial console. I am going to have to, I think, change a bit of code. Yes, because I'm connected now to pin A0 and not pin A5. So we'll re-upload that, open the serial monitor, and let's see. So with this, casually near the candle, I'm seeing values of, I would say the lowest I'm seeing is about 500. As I get closer here, the highest I'm seeing, isn't that interesting? It's inverted, which for the point of our code is actually what we want, right? We want a smaller delay, the lower the reading value is, so it lines up with the potentiometer. But it looks like something between, I had about 700 there when it sort of pointed down. Ooh, that's interesting. So maybe my high value is 950 and my low value is 170. So let's see here. So coming back to our code that we are actually writing, I'll come into my map function here, and I'll say, take the read sensor value, which is between 150, let's say, and 950, and map it to 0 to 1023. Now, here's the danger of doing something like this, is that this map function won't natively constrain this value. So I'm saying, hey, you're expecting to see a value between 150 and 950, stretch that out to 0 to 1023, right? If this read sensor gets a value of 100, 100 is below the lowest range I told it to ever expect, so it's going to hand me back a number that's lower than my stretched range. I'm going to get a negative number back, which is going to cause strange things to happen, I suspect. So what I'm going to do before I just return this raw, I'm going to say int scaled reading equals our map function, and then I'm going to return a constrained version of that integer. So I'm just going to constrain scaled reading 150 and 950. I think that's the right syntax. I guess we'll find out. Constrain will, let's see, scaled reading? Did I just, just a typo. So constrain will say, hey, if this value lies between these two numbers, just hand it right back. Otherwise, cap it to be no less than the first number and no greater than the second number. We just want to make sure that our number doesn't end up falling. Actually, you know what? I'm using the wrong values here. We should constrain between 0 and 1023. Right? So even if this map function ends up with us falling at a negative number or a number higher than 1023, this is going to sort of cap us to that range. So let's upload that. Back to the table. Are you saying we need more fire? I mean, that seems plausible. So now, if I block the fire off, we should see our sort of maximum delay of 1,023 milliseconds. And as we get closer and closer to the fire, we should see things speed up quite a bit. Exciting. That's great. So now we have sort of a rudimentary fire sensor, right? Like this, we can sort of judge the flammability of the nearby objects based on the speed that was cycling through, which for your, fire-related applications might be useful. But what I would really like to have is have sort of 5 ranges of sensitivity where I have too little fire down here, far too much fire up here, and sort of intermediate values in yellow and green down here. It would sort of tell me I'm at just the right range that I wanted to be from the fire. And this, for home application, this is a little silly, but it's a little less silly when you consider, to be like, for example, Brian, I don't think it's a secret to say this, is one of the people in charge of the Science Storms exhibit at the museum that we work at. And there is a really cool interactive called Fire and Water that if there's no fire in it, or I guess, frankly, too much fire, there's a problem. So there are much more complicated sensing systems in that environment, but you could imagine if you were sort of building the same thing at home, you might want to have a sensor that says, hey, is there too much fire, not enough fire, or some amount of fire in the middle? And remember, my fire sensor is just an analog sensor. You can do all of these same demos with a potentiometer or any other analog sensor, or digital one if you develop a bit of math that turns your digital reading into a value between 0 and 1023 here in this read sensor function. And that's kind of the beauty of encapsulating this kind of thing deep into functions, right? As long as this read sensor function gives back a value between 0 and 1023, it doesn't matter to any of the rest of the code where it came from, right? It could be from a digital value that we scaled, it could be related to time. The rest of the code really doesn't know. It's only saying that, hey, this, I'm guaranteeing I'm giving back a number between 0 and 1023, and it somehow reflects the reading on this sensor. So how you get there is up to you. So let us step away from our stepping through just randomly through LEDs function. Let's make ourselves a little threshold sensor that tells us tells us whether there's too much fire or not enough fire or so on. So I'm going to, I think, just delete all of this. Let's delete all of this, and if we bring some of it back, so much the better. I'm going to leave myself a little... one thing I like to do if I'm updating code or changing it is rather than deleting it outright, if I think there's going to be something useful, I just comment it out, so it's still there, but not going to affect my code. For this, I'm afraid I'm going to forget this name, get scaled sensor reading, so I'm just going to leave it on my screen there so I remember what I called it later. So what do we want to happen? Let's write it out sort of in English first. And this is another coding strategy, another coding tip that we've talked about, I think, before, which is writing things out sort of in plain English as you start solving a problem, and then moving on to solving that problem with code by turning that English into code. It's a process called writing pseudocode, which is, writing things out in methodical English and then just simply turning that English into either more English or directly into code. So for this threshold program, what am I going to need to do? I'm going to need to, at some point, read the sensor and light up a light based on the sensor level, right? That's the most basic form of our code, right? That we sort of have laid out as an idea for ourselves. But we can probably get a little bit closer to a little bit more detailed in our pseudocode before we turn it into actual code, right? So this light up the light level based in the sensor, light up a light based in the sensor level feels like kind of a compound idea. We could break this down a little more. So we could say, if the sensor is below, let's say is between certain ranges, turn on a specific LED. So this is kind of a more detailed way of writing out the same idea. I'm just going to put us on a new line so we can read it. Right, so I'm still going to read the sensor, and if the sensor is between a certain range, you want to write the red LED or the yellow LED or so on. But the fact that we now have it's like we've got this if idea in here, and we know that ifs can turn into various statements inside our Arduino code. This already sort of starts to become a more evocative way of thinking about this idea. Maybe I use an if statement, maybe I use a switch statement, lots of possibilities. Let's go one step further before we turn this into actual code just to play this all out. We'll say, if the sensor is lower than the lowest threshold, right? Because I'm imagining in my head I have sort of a list of thresholds we're going to need to hit for these various lights to turn on. Lower than the lowest threshold, turn on the low red light. If the sensor is lower than the second lowest threshold, turn on low yellow light. Aha! So I'm sort of starting to see a kind of an if-then pattern emerge in my code here. And really, I only want to do this yellow light if the red light doesn't turn on, so that's probably an else if. And all of a sudden, this is starting to feel, closer and closer to code and less like English. This can be a really useful strategy for when you're trying to logic out how you're going to set up your code, writing it all out in like this in English, it can be a really useful strategy. So I think we can sort of see where this pattern is going. I'm going to need a series of thresholds, and if it fails to exceed the next one, I should turn on a specific light. So I'm not going to write out the, if we're lower than the next threshold, we should be green. If we're lower than the next threshold, we should be yellow. Otherwise, that might be useful. Otherwise, turn on the highest red light. And otherwise, might as well be an else, right? So I have the sense that I'm going to have 1, 2, 3, 4 if statements and an else statement after it, but depending on some thresholds. So what should we do next? Let's make ourselves a list of thresholds to sort of hold that value. And again, I could write this as individual variables, but it feels like if I have 4 thresholds sort of doing a similar thing, I can probably encapsulate them in an array and use it to sort of handle things a little more smoothly. So let's say const int thresholds equals, and I'm just going to kind of have to guess to start with, right? What feels good. I said my lowest value that I was seeing is about 150, and my highest I was seeing was about 950. So let's say 350, let's see, what's my 500, 600, and 800 will be my various thresholds. I'm going to want a threshold sort of in between each of my LEDs. And if I'm on the outside, I sort of have 4 LEDs, so I have 5 LEDs, so I sort of have 4 boundaries in between them. So I'm going to choose to say that this number of thresholds should be 1 less than num LEDs. Right? And that sort of makes sense. Like I'm going to need 4 transitions between the 5 LED states. It might be nice to make a note for myself of this here, because my math later on might depend on that fact. I might break things if these things are not true. So I'll make a little note to remind myself of that. So now I have my list of thresholds. Let's see what I want to do with it. So I'm going to uncomment this and say interval equals get scaled sensor reading. And maybe a better name for interval, since we're not really going to use it to control time anymore, maybe we want to change that to something else. So I'm going to use one of my favorite functions in the Arduino IDE, the find and replace function. I'm going to replace interval with reading. And I'm going to do replace all. And so now, rather than have an integer called interval, I have an integer called, or I have a long actually called reading, which is very helpful. So the reading is going to be my scaled sensor reading here. And let's do some things with it. So let's start turning our pseudocode into code. Well, we've already read our sensor. That's great, right? Read the sensor. The reading is the sensor reading that we've got. Let's start turning these English statements into code. If the sensor is lower than the lowest threshold, turn on the low LED right. Well, let's just get that out on paper. So if reading is less than the lowest threshold, so that'll be the threshold in position 0, then turn on the low LED light. So we'll digital write LEDs 0 high. That'll turn on the lowest LED right. All right, so that's our first statement here. And I'm actually going to leave this English in the comments in the code, so we can sort of tell what each statement is doing along with the sort of English text here. Right? So, all right, so that might be our first bit of code. If the sensor reading is lower than the lowest threshold, turn on the lowest LED light. All right? Else if, otherwise, else if the sensor is lower than the second lowest threshold, reading is less than threshold 1, it's the second lowest threshold, turn on the low yellow light. So that was our digital write LEDs 1 high. Right? And now I need to do the same 2 things for our green and our yellow. So I'm just going to write those as well. So else if reading is less than threshold 2, digital write LEDs 2 high. Else if reading is less than threshold 3, digital write LEDs 3 high. Otherwise, what was my final otherwise statement? Otherwise, turn on the highest LED light. Else, digital write LEDs 4 high. All right. So that is our pseudocode turned into actual code, right? So we sort of thought through our various how its code would play out in sort of in English, in pseudocode, and then we just went through and sort of typed that up into an if then else statement. At this point, right, the sort of the goal is to get things working. I don't really care if it's as clean as possible. I don't care if it's as compact as possible or expand. I just want to get the thing working because we can always make it cleaner later. So let's upload that code and see what happens. Oop, I have an error. What is it telling me? Threshold. Oh, I didn't call it threshold. I call it thresholds, but I think I'm just going to change the name to threshold. Upload that. Oh, why do I have a typo? Threshold was not declared in this scope. Did I typo it again? Threshold? Threshold. Oh man, I'm going to have a real hard time typing threshold over and over again tonight. Yes, I've written threshold multiple times in here, so that's going to be really quite good. All right, so that is now uploaded. Aha, good. It doesn't work. We can do some debugging. So you'll see it's not quite giving us the same behavior, that sort of behavior that we wanted. If I'm seeing no flame, you would actually have all 5 LEDs on, and as I get closer to the flame, well, now nothing is happening. But if I reset, I sort of suspect that I'll start with 1 LED on, and then 2, and then 3, and then 4, and so on. Right? And they're not turning off because, of course, there's nowhere in my code that I told the LEDs to turn off. So let's be a lesson. Pseudocode only gets you so far, right? Because it can miss some of these little implementation details, like not when I said in English, if the sensor obeys the certain properties of the threshold, turn this LED on. What in my head I meant is, if it's lower than that threshold, turn that LED on and only that LED on, right? It's sort of a slightly more specific example, but of course the code is very literal. So it only turned on, it turned that LED on that I told it to, and then left it on the ever because there was nothing that told it to turn off. So how are we gonna solve that problem? Well, here's the way I think I'm going to solve it. There's a couple of different ways. One is you could write in individual digital write statements into each of these if statements that turn off all of the other LEDs. That would be one way to do it. What I'm going to do is instead write a function that turns all of the LEDs off, and then we'll turn the one that we need to back on. So let's write a new function. It's one we've actually written before in some other bit of code. I'm going to call it all off, and I'm going to say for int I equals 0, I is less than num LEDs, I++, digital write, LEDs, I, low. Right, so a simple for loop here for int I equals 0 through number of LEDs. So for each LED, digital write to it, LEDs at position I, low. We'll just turn them all off. And inside each of these threshold items here, I'm going to turn off all of the LEDs, and then we'll turn back on the one that we care about. Right? This is not, like I say, not necessarily the cleanest way to do this, but right now I'm just sort of interested in getting the behavior that I want. We can always make it cleaner later. I guess that's sort of like one thing as I was thinking about prepping this like writing good code thing, is it's not about writing good code right from the get-go. It's about like writing code that works and then making it cleaner for yourself in the future. I seem to have stalled on upload. That's weird. Let's see here. What is happening, computer? Help me out here. Laura Richardson's here. Hi, Laura. How are you? You could have used a fire sensor at Fisherman's Wharf. Yeah, Laura's out in California, sort of near where Kenneth is. They had a huge fire at Pier 45, I want to say, in San Francisco. Really scary, to be honest. All right, let's see if this will upload now. Oop, an error occurred on Java handler. Oh, this is the kind of thing that usually means I have to reboot my Arduino IDE. Oh, but maybe we're lucky today. I told you things might go a little bit off the rails tonight. It's certainly possible. Oh, we uploaded just fine this time. All right, so yeah, there we go. So now, as we're sort of getting variable levels of sensing, now I have too much fire. So, is anyone observing the same thing I am here? If I'm seeing no fire, I have my highest LED. If I'm seeing a lot of fire, I have a lower LED. So really what I would like is actually to reverse these threshold values. I want the low to be less fire and the high to be too much fire. So I'm going to just reverse my logic here just a little bit. Let's see, how do I want to do this? I could either somehow make these a greater than statement, right? I could say if reading is greater than, or I can just reverse which LEDs I'm using. I think I'm going to reverse which LEDs I'm using. 3, let's see, this should be 4, this should be 3, this should be 2, this should be 1, and this should be 0. So I saw that I was having sort of reversed LED behavior, so I'm just going to sort of reverse which LEDs turn on in which states. It's a little bit of like feels like a little bit of a kludge, but it's actually, I think it's going to work just fine. So now when I'm not seeing a lot of fire, I have a too little fire indicator. As I get closer, let's see if I can balance how much fire I'm seeing right in that beautiful green range. We're getting close. Seems like a little too much fire, a little too... My threshold for that middle range is very narrow compared to what the fire is able to put out. Or reverse the array could certainly do. Or reverse the array. Ooh, Chris, I like the way you think. Let's do that. This is why we do these things. Yes, Chris's suggestion is just to reverse which LEDs mean what. So I can say 13, 12, 11, 10, 9. That's great. Because what I like about that is that now my threshold values and my LED indices are still the same. And I like that a lot because I think it's going to allow me to do some clever things later to sort of make this even more condensed. Right? So now still should have the same behavior. Another good example of do the same thing in a different way, right? To sort of build capabilities, right? I've changed nothing in my capability from a moment ago. Right? I'm still sort of seeing I have too much fire if I'm that close, and too little fire, I suppose, if I'm far away. Let's see if I can get this to sort of stay in a nice stable range here. Yeah, sort of just the right amount of fire there. Just the appropriate amount of fire right there in the middle. So that is the gist of our sensor. We're using a series of if-then statements. If the reading is below a certain threshold, turn everything off and turn on a specific LED. And otherwise, just continue comparing it to the next threshold higher and higher and higher, and so on. So our appropriate LED turns up. This would the very narrow range of acceptable range of fire. Yeah, it's true. It's like we've made it sort of very tight there. But that is the basics of our sensor program. The thing I'm sort of seeing here, and it might be a little too premature for optimization, but one thing that's seeing is like, if you're ever doing the same thing multiple times, it's an opportunity to usually to pull that code out into a function to make things a little bit simpler, make them a little bit cleaner, a little bit more readable. Because right now, to sort of grok all of what's going on with these thresholds, I have to read through a not insignificant number of lines of code. What I'm seeing is each of these statements is an all-off followed by a digital write. They're all sort of the same, all-off, digital write. So that feels to me like an opportunity to sort of cop that out into a function that'll make things cleaner. So let's do that. So I'm going to write a new function. I'm going to call it void set output state. And I'm going to make it take a number. Say int LED on. And all it's going to do, I'm going to copy and paste from some earlier code. All it's going to do is turn off all the LEDs and turn back on the one indicated by LED on, right? So I'm going to hand it an integer to turn off all the LEDs and then turn on the LED indexed by this LED on variable. And what that's going to allow me to do is, right, because this is just a couple lines of code here, I can use this to replace these pairs of lines of code. Set output state for in each of my if then else blocks, right? So this right here, all off and turn LED 3 on, just becomes set output state 3. And this block of code here becomes set output state 2. And this block of code here becomes set output state 1. And this block of code here becomes set output state 0. I'm just gonna, I think now that we've sort of got things working, I'm gonna remove some comments there. And now we're sort of seeing like, look how much condensed this is, right? If we're less than threshold 0, set output state 0. If less than threshold 1, set output state 1. Now, if we wanted to, I think the next logical like jump is we're seeing like, oh, I have 0 and 0, 1 and 1, 2 and 2. Could I condense this into like a sort of a lookup function that says if I'm less than a threshold with a given number, turn on the output state with that given number? I could. Feels a little bit premature, but again, if I had, say, 100 thresholds, I wouldn't want to write these all out by hand. So I'd probably figure out some way to wrap this up into a for loop or something like that. And we might do that later tonight. It just feels like a little bit premature. Like it maybe is more than we need to do right now. So not going to worry about it. This is all like, I hope you're taking away that like writing code, like what makes good code is a lot of just like, what do I need it to do right now? Do I need it to sort of be cleaner and smaller? Maybe I condense some things into functions. Is it easier if I just leave things spread out because it's working and I don't really care right now? Sure, leave it spread out. Doesn't really matter. Sort of a matter of taste and need at any given moment, if that sort of makes sense. So, because what I want to do, rather than sort of focusing on like condensing this code, which is working just fine, what's bugging me at the moment as I'm seeing it in my peripheral vision, is this flickering. Right? I have this like, I'm seeing varying amounts of fire at any given moment, and it's not actually great. Chris says, I feel like it makes sense here, and I get to actually looking at my code. Yeah. As always, like, you know, talking about code is a little bit like dancing about architecture. Like it's not quite the best idealist learning vehicle. Ideally, we'd all be together in a classroom, and I'd be leaning over your shoulder and typing on your keyboard and breathing down your neck. And all of those things are verboten right now. So this is what we kind of got. Or we can do like what we did on Thursday, and we found out that on Zoom you can doodle on other people's screens as they're screen sharing. So Mike and I were trying to debug some of his code, and I could just come in with a little pen and be like, look at this line right here. Look at this function. What if you did this instead? And that actually worked out pretty well. So I think there are clever ways to sort of be safe and do code right now. But if it's all a little bit opaque, I don't count on that we found the most perfect vehicle to talk about code just yet. In fact, I'm gonna call an audible and actually skip that averaging thing I was gonna do next, because as I think about it in that context, it is interesting, but I think it's gonna be more reading code at y'all, and I think I'd rather sort of introduce a new structure, which I think will be more useful in the same way that I think like thinking about like how this watch the clock pattern is equivalent to doing this delay function, but without locking up your program. I think maybe I want to skip ahead in the lesson plan a little bit and talk about program modes, because I think that will be a little bit less reading code and a little bit more broadly applicable. So, as always, thank you for where are we? Here we are. Thank you for bearing with me as we figure this out together, like how any of this is actually good and interesting and useful. I also wish, as long as I'm tangenting, and I should drink more beer, as long as I'm tangenting, I wish there was a way that I could be coding here and y'all could be watching live in your own, you know, on a website somewhere, like a kind of like a Google Docs style thing, but that was also an IDE, so that you could be watching me code, I could upload it to my board, you could upload it to your board, or something. It's not a fully fleshed out idea, but I feel like looking at the code on somebody else's screen as I scroll around is like not quite perfect. If anyone knows of a thing out there that's kind of like that, I mean, Google Docs or Google Wave are kind of the closest that I know of. Anyway, that's where my head is at the moment. But let's talk about program modes, because it's actually going to be a pretty short departure from where we have already been. So we have our fire sensor working, right? It's in fire sensor mode, let us say. Let's add a mode where let's see, how do we want to do this? What should transition us between modes? Oh, I know. Let's say if the level of the fire is way above a certain threshold. Like, let's say these are sort of our standard states, but let's say if we get way above or way below the lowest, we want to go into alarm mode. And alarm mode will do something. We'll come up with it in a second. Maybe it flashes the LEDs. Maybe I think about a buzzer. Maybe it buzzes some buzzer, and maybe it does that for. Could be a certain amount of time, or maybe until you press the reset button. Maybe that's there is a fire button, or there is definitely not a fire button, which I guess maybe it's only a high threshold. Maybe if there's so much fire that we're way above our high level, we go into this other mode until something. That seems like a plausibly useful for a fire sensor here. And for your sensor, like if it's a distance sensor or a water level sensor, like certainly for like a water level sensor, too high or too low are also, you know, probably useful states to know about if you're doing water level in a a plant bucket or a cistern or what have you. But yeah, let's implement a too much fire mode, because it's actually not going to take that much additional code, and I think it'll be more interesting. So here's what let's do. So, you know, we're going to have, let's say, a couple of modes to think about. So we're going to need some way to remember what mode we're in. Well, let's add a variable. Let's say, I'm going to say, I'm going to make it an integer, just so it stores it as a number, because that means it's going to have lots of possible values. I could use, if I was confident I was only ever going to have two states, I could use a Boolean. I could have a, you know, are we in alarm mode variable, and that could be true or false. But I'm sort of thinking that, like, this might have alarm mode, sensor mode, averaging mode, go to sleep mode. Like, there could be other things. So I'm going to choose to store my current mode as an integer, just because that gives me the possibility to mix it up later. So I'm going to say int current mode will be the variable that holds what mode I'm in. And I'm going to define a couple of numbers that are going to represent the modes I could be in. So let's say int, let's see, and I'm gonna make these sort of constant-y things, because I don't want these particular numbers to change. I'm gonna say mode sensor equals 0, int mode, what do we call that? Mode alarm equals 1. And I'm gonna say when my code starts, current mode is going to equal to mode sensor. I will say, so I will say a lot, I think, yeah? Drink every time I say I will say. There is a structure in code, and was reminded of it by Michael Trudeau's code the other day. There is a structure called an enum in C that is meant for exactly this kind of thing, holding a sort of a list of text tags that represent discrete numbers so you can sort of switch between them. And you'll see it in a lot of example code out there on the internet, because it's essentially, you know, if I have lots and lots of these different modes, there is a way to sort of wrap them together in a way that defines them more easily. The Arduino IDE kind of messes up how it handles them in a way that I don't want to go super far down the rabbit hole tonight. Just know if you see an enum, you can do this. There's another way to sort of store like various modes or various states in a slightly more compact way. It works exactly the same. I'm not going to use an enum tonight. Enum is E-N-U-M for like an enumeration. But just know if you see that in an example code, that's a perfectly fine way to do it. I'm just not going to go down the rabbit hole of doing it this evening. So I've defined that mode sensor, the sensor mode is 0 and alarm mode is 1, and my current mode is going to be the sensor mode when we start. So in our theme of tonight, of doing the same thing in a slightly fancier way, I'm going to first start by saying, in my loop as I have it currently, I'm going to wrap the whole thing in an if statement. I'm going to say if current mode equals mode sensor. New set of curly brackets, and then I got to come down here and close them off. I'm going to select all these lines and indent. I'm a little bit of a stickler about my indents, so we'll indent that over. So now this is my whole for loop from before, is like wrapped up in this if statement. And because my mode is I'm in sensor mode, I'm in mode sensor, and I'm not going to change it anywhere in my code, this should work exactly the same as before. Chris says example or real code. Excuse me. Oh, Chris, are you asking whether the enums show up in example code or real code? It shows up in them both. All I meant to say was, if you're looking at examples of doing something like this online, excuse me, you may find enums used as an example. You'll see them used in real code, in application code for sure as well. I just meant the code that you might be using as an example. But it is a good thing to use, it's a good structure, and really it's just that the Arduino IDE itself kind of screws them up in a way that makes them just a little bit cumbersome to use, but it's a perfectly valid structure if you want to go to the trouble. Thankfully, as we uploaded in the meantime, I'm doing the same exact thing I was doing a moment ago in a slightly more complicated way. So nothing has changed because we're in sensor mode and we're always in sensor mode. So the code that says, if we're in sensor mode, do a thing, does a thing. Super great. So this now lets us do something else. So now here's the end of that if statement. Mode sensor, matching parentheses, good. So I say, else if current mode equals mode alarm, we'll do alarmy stuff. I'll put that in a comment for now. And again, this shouldn't do anything because we have no way of getting into the alarm mode, right? But it can always be nice to check, like, this shouldn't do anything, and it doesn't do anything. That's great. So before we figure out what the alarmy stuff is, let's figure out how we're going to shift into that mode. So we said if we have far too much fire, we're going to shift into that state. So I actually need a new highest threshold that's going to be my too much fire threshold. And now, so that's going to be my below this number LED 1 is on. In between these two numbers, LED 2, LED 3, LED 4, LED 5, and alarm. I'm going to update my comment here. It should be number of thresholds equals number of LEDs. I need to update my if then else code here because I'm only measuring if I'm less than the first 4 thresholds. Now I need to check if my reading is less than threshold 4. Set output state 4. Else, so if I'm not less than any of my 5 thresholds, I'm in my highest state. I want to say current mode equals mode alarm. Will shift us into alarm mode. And just so we can see what's happening, because we have the function already lit, let's call our all off function. Now you notice I have no way to get out of alarm mode currently, and honestly turning everything off is probably not the best for an alarm function. Maybe we make an all on function that we can actually tell when something's going wrong. So I'm going to copy and paste my whole all off function, make a new function called all on, and I'll write all of my LEDs to be high. So same thing, stepping through all my LEDs, making them high. That'll be my all on function. And that's what I will do if we are in alarm mode. So all I've done is wrap my whole loop in an if statement. If the mode is in sensor mode, do one thing. If we're in alarm mode, do a totally different thing. So let's upload that. Oop, typo. Threshold. Alarm mode is call Kenneth. If there's too much fire, is Kenneth really the one you want to be calling? I guess is the question. Let's see here. Ooh, it seems like we went into alarm mode awfully fast there. Why would that be? Interesting. Oh, you know what it is? Aha! Yes. So, I should be going into this. We saw low values when we were close to the fire, and high values when we were far from the fire. So really, I want to be in alarm mode if I am very, very low. Aha. So how am I going to change this? Let's see here. So I'm going to change this all to greater than. So really my alarm functionality is not at this high end of this range here. It's at the low end of my range. Remember, close to fire means low readings. So really, I really want my first LED to be on if I'm between... Oh, you can't see. I'm so sorry. I want my first LED to be on if I'm between 200 and 350. My second LED between 350 and 500, and so on. So I'm going to say if LED is greater than threshold. I have to reverse everything again a little bit. Turn on output 4. Else if I'm greater than threshold 3, output 3. If I'm greater than threshold 2, output 2. If I'm greater than threshold 1, output 1. If I'm greater than threshold 0, output 0. And if I'm less than any of them, go to alarm mode. That's the way that logic reads. Oof, a little bit torturous there. I hope reading out just a random list of numbers is an interesting thing to do on stream. I sort of suspect it isn't. But now we see we have our sensor mode back here, right, where we're sort of sensing the amount of fire. Hopefully, as we get close enough, yeah, there we go. We went into alarm mode, where everything is just on. Now, of course, we don't have any way of getting out of alarm mode, so we'll have to add that in as well. So let's see. What should we... how should we get out of alarm mode? If we detect too much fire, and assuming we don't have a SIM card module to call Kenneth, what should be our our way of getting back to normal sensor mode in this application, I suppose. Lack of filtering. It's so we don't have any. If the moment we peak above our high level, we see a lot of fire, we're gonna go into alarm mode. Michael says, "Call Mary." Honestly, that would be the most genuine answer. Is call the wife if there's too much fire in the office. Buzzer until Mary comes. Ken says, "Stay in alarm mode for 2 seconds." I like that answer a lot because that can kind of blend the two things that we have done tonight. So let's take that answer. Chris says, "Buzzer until Mary comes." Press both buttons. Also, let's do the time one first, and then we'll do press both buttons as well. We could also do either or. That might be kind of fun. Maybe it's, stay in alarm mode for 1 minute until you press both buttons. So let's see. So what I'm going to need here is, so right now, if current mode equals alarm, all on, I need some way to transition back to my other function. So I'm going to say if some condition that will come up with a moment here, current mode equals mode sensor. I guess the whole point was to try and read out code out loud and talk at you more. I guess this is what to take away about switching modes. It's basically creating multiple sort of if blocks based on what mode you're in, and then within each of those doing something different and incorporating some code that switches a variable that tells you what mode you're in. So right, in this one we had us, doing a variety of things and reacting to our sensor state. We changed our current mode. Now in our alarm mode, we need some code that switches the current mode again. So we're going to wrap everything in an if block based on what mode we're in, and then within that if block, we just need some code to tell us when to switch between modes. So let's do some work on populating this if then statement. Travis' idea. What about going into alarm mode if there's too much fire for more than 2 seconds? We should do that as well. Let's do getting out of alarm mode first, and we'll add that in later because that's good. This is building functionality onto this stuff. I like that a lot. So let's see. If we're in alarm mode, we'll turn on all the LEDs, and then we really just need to, what do we need to do to see if we are going to drop back into sensor mode? Let's do Kenneth's example of if we're in it for a certain amount of time, then we'll drop back into sensor mode. So let's define first a variable to hold what that's going to be. So I have my reading variable here that's up before. I'm going to say long time to stay in alarm mode. And that's a pretty long variable name. You can obviously choose a shorter one for your code, but for the sake of verbosity, so we all know it's, in fact, let's just call that time to alarm. We'll call it 200 milliseconds to start. Since we're working with millis a lot, let's just say that this value is in milliseconds. And this is going to be very reminiscent of our time to check the clock pattern. I'm going to need a variable to hold when my state changed. I'm going to say time alarm started equals, let's say it starts at 0, just so it has a value for us to start with, right? So much like our check when the cupcake should come out of the oven function, I'm going to say that the time that I go into the alarm state is when I put the cupcakes in the oven. I'm going to say that the time alarm started equals millis. So remember what time we went into alarm mode, because I'm going to need to check if we are more than 2 seconds past that time, right? So time alarm started, we'll record the time we go into alarm mode, and then we'll say if millis, the current time, if millis is greater than the time alarm started plus time to alarm, right? So the time the cupcakes went into the oven plus how long it takes to bake cupcakes, then transition back into our other mode. Cool? Is that feeling very familiar, right? So this delta time idea can be used for things that recur or things that only happen once. The principle is exactly the same. So now I'm here in sensor mode that we know so very well. Aha, it's already working. So as I go here, I'm going to block it off so I can get close to the fire. We'll trigger there. We'll go into alarm mode, and then 2 seconds later, our millis function will be greater than the time that things started plus the amount of time we're supposed to wait, and we will drop back into sensor mode. Does that sort of make sense? That's a kind of a revisiting of our idea earlier tonight. So rather than constantly, rather than updating this time, the time the cupcakes went in the oven, the time that we last checked on the baby, whatever our metaphor is at the moment. We said it. We said, hey, this is the last time that we changed state. Let's just keep checking if we're more than the amount of time we were supposed to wait past that state. And of course, if we change our sort of timeout here, our alarm time was 2,000 milliseconds. If we change it to 5,000 milliseconds, we can get a similar result, but for 5 seconds. So if I trigger my alarm mode, 2, 3, 4, 5, and off. Right? So that's one way of getting out of the alarm state, and a pretty functional one. So what we've learned is if there's too much fire, we have 5 seconds of alarm, and then everything relaxes. It's all fine. Which is fine. Maybe not an ideal fire alarm. Maybe we want to make that value a little bit longer. But that's all right. That's totally cool. Let's incorporate Palmer's idea now of it will reset after a certain amount of time or after both buttons are pressed together. Either one of those things will take us back to our basic sensor state. So let's go down. So we're talking about ways that we're going to transition from our alarm mode back to our sensor mode. So somewhere in this if statement, I'm going to need to sort of add another condition. One useful thing can be, so like we could do this all inside this if statement and add more statements out here, but it's gonna get a little bit unreadable. So when I have sort of multiple conditions going into an if statement, I like to break things out a little bit into sort of multiple combinatorics. So I'm gonna declare a new Boolean variable. I'm gonna say Boolean is alarm expired equals, and I'm gonna use this true or false statement down here. Say is alarm expired is equal to, can I do this? I actually don't know this is the right syntax. Let's find out. I think I can do this. Yeah. So what's happening here is, this expression, millis is greater than this, is either true or it's false. And we're going to store that truth or falsity in this Boolean variable. Is the alarm expired? Well, it'll be true if millis is greater than this amount. It'll be false if millis is less than this amount. So I can say Boolean is alarm expired, right? And this is exactly what we were doing before. Another example of do the same thing in a slightly more complicated way, right? Before we start building on this double Breton press idea, to sort of, as you're breaking things apart, it takes so little time to upload code to an Arduino that there's really no disadvantage to sort of testing as you go. And we can see alarm mode is still working as before. And after 5 seconds now, we time out, we're back in sensor mode. Glad that worked. So now that we sort of have broken this out here, we could add more Boolean variables that would sort of help control our behavior. Let's do a new Boolean called are both buttons pressed. That will be true if and only if both buttons are pressed. So how would we do that? We will say be a combination of two things. If digital read button 1 is low, because remember those buttons are pulled high by that input pull-up type, and they'll be low when they're pressed. But true if the first button is low and digital read button 2 is low. We've seen this this double ampersand symbol a couple of times now. But this is a logical and, right? So this and this. So this value, this are both buttons pressed is true only if this side of it is true and this side of the double ampersand is true. Single ampersand means a different thing. You want to use a double ampersand when you're working with logic. So this will be true if button 1 is low, is being pressed, and button 2 is low, is being pressed. So now I have this Boolean, this true or false value, that represents whether both buttons are being pressed. And I can once again use that double ampersand expression to say if the alarm is expired. Okay. So I can say if the alarm is expired and both buttons are pressed, exit current mode. So what'll this do? So this will mean I have to wait at least 5 seconds and press both buttons. It's not quite what I meant to do, but it's kind of interesting. Upload that. Right, so now when I trigger based on fire, when I wait 5 seconds here, nothing should reset, right? Because it's going to be waiting until both buttons are pressed. When I press both buttons after 5 seconds, we'll see reset to sensor mode. When we trigger again, if I press both buttons soon, nothing will happen. But if I hold them down here, then after 5 seconds, be reset. We're using that logical and to sort of combine conditions for whether things will change. And that's not quite, Palmer, what you suggested, which is, or what I'm interpreting what you suggested to mean, which is, waiting a certain amount of time or pressing some reset buttons. That actually feels a little bit more to me like how a fire alarm or like a burglar alarm in your house might work, right? Like it's going off for, 5 minutes, or you can run over and press a combination of keys. So in this case, I'm going to use another logical operator, which is these two vertical lines, these two vertical separators here. That's a logical OR. So that'll be true if this side is true or this side is true. So is the alarm expired or are both buttons pressed? If so, we'll go back to sensor mode. So coming back to the table, uploading, back in sensor mode, we can see now we can trigger the alarm and we can wait our 5 seconds for our timeout. There we go. Or we can trigger it, and anytime we press both buttons, we can see it resets to sensor mode. And that's because of this logical OR that we're using in here. This has become a little bit of a logic lesson, right? Using this logical AND to combine two true or false values, and this logical OR to combine two true or false values is kind of a useful thing. It's got a little bit wordy, but this is the gist of switching between, remember, we're talking about switching between modes of operation. And the gist of it is you have a variable that holds what mode you're in. You do different things inside of your different if blocks based on what mode you're in. And then you just need to figure out some code that tells you when you want to switch between each of those modes. Make sense? Questions, comments, issues, concerns? Can I suggest using the shit out of parentheses? Not a bad idea to keep things clean. I don't use them quite as heavily. It's sort of a matter of style, but using extra parentheses can't necessarily hurt. So it's not necessarily a bad idea. I will just digressing as I see if there's any questions or comments or suggestions of what to do next to this bit of code. But I think this is a scentless candle. I've been trying for like the past 30 minutes while writing code to try and figure out like what am I smelling. Nothing. I don't think I'm smelling anything. A little fruity. A little bit like effervescent. Not quite sure. Very strange. You're not close enough? I go, yeah, we'll get... Yeah, how many cameras can I get the fire in at any given time? I don't intend to light my beard on fire tonight if I can help it. I would have to call Marion at that point. Let's do one more example of a thing, just because I think it might be interesting and inspire some things, and it will be a little bit more reading code at y'all, and for that I apologize. But Travis, you had a thought about, could it go to alarm mode only if we were at that highest level for more than 2 seconds, which is kind of an interesting idea and might lead us down an interesting code path. I've lost my sense of smell. Yeah, after enough time in this room with the 3D printers and the hot glue guns and everything, it might have happened, but we shall see. Taste is good, thanks to this Scent with Lasers IPA from Beguile Brewery here in Chicago, Illinois. That's so silly. Let's check out this idea of like alarm if and only if we've been in our highest threshold for more than 2 seconds. So, and to be honest, I haven't quite thought through all of what that would mean. But I know that this is the part of my code where I'm changing modes, right? So somewhere in here, this is going to be not just like if we're lower than our lowest threshold, go to this mode. Something else is going to have to happen in here, right? And I'm probably going to I'm still going to need this, right? It's going to still have to remember what time I went into alarm mode. So we'll keep that, but this is going to have to change. And since we're going to measure time, I'm going to start by creating another couple of variables to track some time. So I'm going to say long time went to time, I don't know, fire time. So and that's going to be the time that the sensor went below our lowest threshold. So basically, it's just another way of saying that the sensor has been in the alarm range of the sensor for more than 2 seconds, is saying that it goes into that range, and then it continues to remain in that alarm range for 2 seconds. I think that's basically saying the same thing. But what I'm going to do is going to need to sort of, when we first reach that alarm range, I'm going to need to remember that time and then continually check if I'm still in that range. And if I am, then if I'm in that state for at least 2 seconds, I should jump to alarm mode. So I'm going to need a variable to track when I enter that state. Time start being in fire range. That's a really verbose variable, but that's okay. And long, I don't know if I actually need a second variable here. Let's see. Yeah, let's see. I might have to think this through as we write the code for it. So, let's see. Oh, I'm gonna need to track whether my previous step was inside the fire range or if I'm just entering the range where I'm seeing maximum fire, so that I can know whether to start this timer. So my Boolean is seeing fire. So this else statement here is seeing maximum fire. If I'm below my lowest threshold, I'm seeing as much fire as I can see, right? So if that's the case, if I'm seeing as much fire as I can see, if is seeing fire is false, if I wasn't currently seeing fire, then I should say is seeing fire is true, right? I've just started seeing the fire, and what the hell was that long-ass variable name? Time start being in fire range? What a nightmare of a name, right? Equals millis, right? So whenever I transition from being below, outside of the range of maximum fire to inside that range of maximum fire, set a flag, set I'm seeing that fire now for the first time, and set the time. If I am not just seeing fire for the first time, right? If I was seeing fire last time, so this is really seeing fire for first time in this loop, right? Because if I'd seen fire in the previous loop, is seeing fire would already have been true. If I'm not seeing fire for the first time, then I'm going to do my watch the clock method. If millis is greater than time, this long-ass variable name, time start being in fire, plus, I need a variable to tell me how long I'm supposed to be there. Let's say long fire trigger is 2 seconds, 2,000 milliseconds, right? So time start being in fire plus fire trigger, then current mode equals mode alarm, and time started equals millis, right? I think that's right. So let's think through this logic again. So, right. So I'm passing through my loop over and over and over again. If I'm in the maximum range of seeing the fire, if I wasn't previously seeing the fire, remember that this is now the current time, the first time that I'm being in this fire range, and is seeing fire is true. But if here's what I need. I need some way to set this variable back to false. So really, in each of these other sections, I should be setting is seeing fire to false. Oops. Equals false, equals false, equals false. There's probably a cleaner way to do this. So now I've got a lot of repeated code here, which I don't really like. So what will happen is if we're seeing fire and then we start to not see fire, we'll reset this variable. We'll reset this is seeing fire variable. The next time we start seeing fire, we'll reset our counter to the time that the fire first appeared. I think that makes some sense. Let's see. Is seeing fire equals false to start with. Not too many typos this time, so that's a good sign. While that's compiling, what questions do we have here? Further reading for this filtering concept is digital signal processing is a whole thing, and also I should say this is a really decent strategy for if you're handling only a couple of modes or 3 or 4 modes, maybe 5. This is a pretty reasonable way to handle mode transitions. If you were writing something that had lots and lots and lots of potential modes, or states, you could also think of them, various states that the program exists in, the sensor state, the alarm state. There are patterns that clean up the transitional logic a bit, The example that springs to mind is if you're making, say, a video game character who might exist in the standing still state, or the walking state, or the running state, or the jumping state, or the slashing at sword. They might have many of them, and each one might have slightly different logic for, you know, what buttons you press to transition between various actions and motions, and which ones are allowed and which ones not. There are ways of wrapping those transitional bits of logic into a slightly cleaner function, so you don't have to remember which timers to set for which transitions to which modes. For our purposes, this is a perfectly reasonable approach to take, if that makes sense. Let's see if it works, I suppose. So, what do we say here? So if I get near the fire again, see if we're seeing maximum fire for at least 2 seconds. I have to sort of hold it right in the fire there. See if we're going to alarm mode. We don't seem to be. It's also possible I'm just not close enough to the fire. I might have to turn down that fire threshold a little bit. Let's see. We'll turn up that fire threshold. Let's set that to 300. There we go. See if we see that fire. If it doesn't work, we'll get to do some juicy debugging, which will be great. You know what I really should do? I'm gonna so good debugging example. Something is not working. I knew we were going too well. So things I might choose to do is right now I'm gonna turn the fire trigger variable way down. Right. So I'm part of the problem is I'm dealing with physical phenomenon here. So I've kind of got to start guessing what's wrong. So I'm gonna do. I could do a whole thing on debugging as a thought process in general, but my heuristic is if you have some reasonable potential candidates, some low-hanging fruit, pick them first, and then as soon as you've picked them, move to a more methodical method. So right now, I'm guessing I'm just not seeing maximum fire for long enough, so I'm going to turn my threshold up, I'm going to turn my trigger time down, and see if that gets us there. And if not, we'll see what happens. Yeah, I would guess something is bugged. Haha, okay, so that's exciting. So let's see what that bug might be. Let's think through our logic one more time of transition. Let's see if there's an obvious error in my traditional logic. So if seeing fire is false, set seeing fire true, grant time being ranged method in millis. If the current time is greater than time being of fire trigger, current mode equals mode alarm, time alarm started equals millis. And that should all work the same. One thing I might do as a debugging tactic is just start in a different mode. What if I start us in alarm mode here? Let's just make sure that alarm mode still works and I haven't broken it somehow. It seems to still work. Yeah, I did a bad camera there, Kenneth. So alarm mode is still working. It's something about the logic of transitioning to alarm mode. Let's see here. Well, let's see. Let's use the serial monitor to help us out a little bit here. I should point out, so the serial monitor is a really useful tool. The serial monitor, of course, is not free in time, right? It's going to take a little bit of time for the program to get the data out to us. I'm going to do a serial.begin with one of our common serial rates here, 115200. And I'm going to say, if seeing maximum fire, serial.println, what are we going to print here? I'm going to print, what's our sensor reading variable? It's just reading. So we'll start seeing readings appear on the serial monitor once we're in that maximum fire range, and that should sort of start to tell us a little bit about what we're actually seeing. We got some cruft left over from earlier here. Get out of there. Get out of there, cruft. Nobody wants you. Palmer says, investigate options for bigger fire. You know, I have been married for just over 1 year, and I'd kind of like to stay that way, if you don't mind terribly. So let's see. I'm already still starting in alarm mode here, but I'll leave us on fire view. So there we go. So we can see some interesting things happening here. So we're mostly staying below that minimum threshold range, I think, for quite a while. So that's a good sign. So it tells me that, like, maybe the problem is not with the physical inputs. Maybe it's something to do with the logic. But so that basic serial command is sort of good in verifying that we actually are getting the readings that we would sort of expect. Let's see. What do I want to do here? Let's us, instead of printing out the raw reading, let's print the difference between the current time and the time that we started being in the fire range. So like, how long have we existed in this state? Because what it should be is that once the current time exceeds our waiting time, we should go into alarm mode. But for some reason, of course, that is not happening. So let's see. Let's see what we learn here. Ah, I'm not getting anything. So, which is interesting because it tells me that we're never getting to that bit of code, which is in itself a useful data point. That's a, why would we never be getting there? If seeing maximum fire were less than threshold 0, which is 300, and if that's the case, then if we jump in here, because we were running through code here, let's see. Let's just do print seeing max fire. It's just a little taste of the debugging process. Probably not stupefyingly interesting, but maybe useful. Laura, it's a good thought. The thresholds are inverted, so the more fire we see, the lower the number. So right now my fire threshold is at 300, and I'm seeing readings at like 30 to 50. So I don't think it's a thresholding issue. I don't think. I might be wrong. Maybe over the fire or in the fire. Well, that's not quite what I meant to do. But I am seeing, it's interesting, so this seeing max fire code is running, right? And then I take it away and it's not. So that, part of one of the useful things you can do with like a serial print is not just print variables, but like that tells me I got to this point in my code, right? I'm inside this else statement, I was below that threshold, so I got here, but I'm never seeing this code. So for some reason, this code is always running. And then is seeing fire is being set to true. Do I have a rogue? Is seeing, like, is this, that's like, we're getting to this point, so we must be getting to one of these 2 points. It's an if-else statement, so one of these 2 is running. So it must be running this code, because it's not running this code. So why is that? Oh, I found it through debugging. As Kenneth points out, Michael Glass for the win, spotted it way before I did. Yes, I have an equals equals instead of equals. Yes, is seeing fire equals true. It should be true. It's not being compared to true. Oh, nailed it. A+. Yes, well done. Well done, Dad. That's awesome. It's kind of thing I was like afraid that would sort of happen, that I would typo and not be able to find it. And also, like, I don't know, that's very real of like what the process is. Okay, so that's a good sign. I don't know if you saw that there. We got back into alarm mode when we got close to the fire. Now, of course, I turned that time limit way down to 1 second. Let's turn that time limit over in fire trigger back up to Travis's original idea of 2 seconds, and just make sure that works. All right, so we're still starting in alarm mode. All right, so now we're in sensor mode. We're readings. We're changing our thing, being a little closer, right? And now, if we get close enough for 1, 2, get in there. We go to alarm mode. There we go, and everything's on. Now we wait 5 seconds, or we press our 2 buttons, and things time out. It's all working together in concert so nicely. So a little bit of a meandering path to get there, but you can kind of see how this pattern kind of mirrors the pattern that we were using earlier, that like checking the clock pattern. We remembered the last time we did something, and then if the current time is greater than the last time we did something plus the time we were supposed to wait, then we take some action. In this case, it's changing modes. We did need this little extra bit of logic because we wanted to reset our start time. We only wanted this to happen if we had been in a state continuously. And so we were saying, in every other sensor reading, we were saying we're not in that state. But the first time that we enter that state, we set that variable to true. So as long as we're remaining in that state for at least that amount of time, we're not resetting our start time, and so this code is able to run. So sort of an extension of the watch the clock pattern that we were talking about sort of throughout the night, I suppose. Does that sort of make sense? And that also, so like that troubleshooting process is, I would say, now it turned out to be a typo, which is good, but that sort of led at how we got to figuring out where the error is. Because one of the worst things is like your code compiles, it runs, it doesn't do the thing. Well, hell, where do I start? You can do all, when using your available outputs, whether it's using maybe the onboard LED or something like that, or in my case, the serial command, just narrowing down, what are your variables showing up as, or even figuring out like what code is running. Like we got some information because we never really saw this bit of code run. We never really got that value printed out. So we knew that this code down here was not running. So there was some error in the little bit of code that we knew was running. And my dad spotted it first. A misplaced equal sign was the culprit the whole time. Well, dang. Very good. So that I think is the gist of our programming patterns for the evening. I want to refresh them real quick for y'all, for those of us who joined us later, or sort of just to recap where we have been. And again, like I know that these like thinking about code nights are kind of kludgy. But if you take nothing else away, this is how to break away. I think there are so many of you that I have talked to over the past couple of weeks. Some of you who are experienced programmers, some of you who are literally brand new as of the start of this series, which is kind of cool. This pattern, this watch the clock pattern, is a really good way to start taking your code from the intro level to the intermediate level, right? Getting past this delay function allows your code to do a lot of things at once. And this is the basic construct. Rather than doing do stuff and then delay, you need a variable to hold the last time something happened and a variable that holds the interval in between when things happen. Then inside your loop, you check if the current time, as represented by this millis function, is greater than the last time stuff happened plus the amount of time you should wait. Update the last time something happened, and then do some stuff. That is the core of the pattern in there. So I encourage you, if this is the first time you're running across this, or if this series is the first time you're running across something like this, practice using this pattern. Practice using it in multiple places in your code. Practice doing it sort of maybe twice over. Maybe you have one LED blinking with one pair of variables and another LED blinking out of sync with it with another pair of variables, right? Because of course you can stack these things one after each other because they're not blocking each other from operating. A really super valuable pattern. Practice doing it with arrays. Maybe you have maybe you have an array of watch the clock variables and an array of intervals, and they all control different things. Maybe, I don't know, maybe a whole lot of things. But it's a super powerful programming pattern. Continue thinking about how you can set up your inputs to be checked independently, your outputs to be checked independently. Well, here's a little tiny topic. I know I usually say we're wrapping up and then we go on for like another 20 minutes, but I think this will be pretty straightforward. We wrote a few functions tonight, and I know we have written written some functions before, but here's one sort of pattern, anti-pattern that I want to point out to you because I've seen it in a couple of people's code. Here's a really function you probably wouldn't need to write, but as an example, let's write the function _2 that takes an integer and multiplies it by 2. Here's one way you could write it. You could say, I have some global variable called SumVariable. I have a function called ×2 that returns SumVariable times 2. I could also write that function so that it takes a variable at the time that I'm using it and returns that times 2. This second implementation is always going to be more versatile. If you can write your functions so that they accept a variable rather than relying on some variable you define somewhere else, they will almost always be something you can reuse in a useful way. Let me show you what I mean inside of our code here. So I had this, for example, this set output state. Remember, I told it which LED to turn on. It turned everything else off, and and turned an LED on. I could also have, defined a variable somewhere that tracked which one LED was supposed to be on, and this could have not taken a variable. But writing it in this way, where it takes a variable at the time that you use it, is always going to be a more flexible option for you. So I encourage you to look for ways to, if you're using variables inside of your function, see if you can incorporate them into the function definition, because then you can reuse this not just on whatever global variable you have floating around, but at something you're using at the immediate moment. I think I've touched on all these slides and haven't really gone through them, and I also have horrible typos in them. When adding structures, first imitate what you have working, right? So this is the thing we've been hammering on tonight. If you're adding a new function, when we were adding modes, when we were adding extra inputs and outputs, we basically replicated what we already had, so we knew what we were looking for, and then we sort of built on top of that. It's so cheap, it's so fast to upload code. There's really no penalty for, well, I'm doing the exact same thing again in a different way. Let me just upload it and make sure that's true. Because sometimes you'll add an extra equal sign and it won't be true, and you'll make it a lot easier for you to find. Yeah, that's, I think, the thrust of the evening. So the programming tips were: check your inputs first in isolation, check your outputs first in isolation. Arrays are useful. Delay is let me be clear, delay is a really fast way to write code. And when you're checking inputs and outputs and just slamming things into your IDE, delay is great. It's so fast and so easy. But when you're moving into writing an application that has to do more than one thing, and that's an input and an output is two things, think about transitioning away from delay and toward this watch the clock pattern. It really is a powerful way of doing multiple things at once. And also think about, as you're building structures, think about doing the same thing that you were doing before in a fancier way before you build extra functionality in there. Brian says, could you explain return again? Yeah, I'd be happy to. Let's start a new bit of code over here, and I will show you return. Let's see. I'm gonna save this. I'm gonna call this a return example. Let's use. I'm gonna just to make things simpler, I'm going to use the serial monitor to sort of hand us values back, because it'll make things easier. So in my setup here, I'm gonna do serial.begin 115200, right? Give ourselves some serial information to work with. Let's write a new function. So a function is just a chunk of code that you can ask to run by name, right? Setup is a function in and of itself. Loop is actually a function. And the Arduino, when you ask it to run code, what you're really asking it to do is run the setup function once, run this chunk of code in between curly braces once, and then run the loop code over and over and over again until the heat death of the universe or you pull the power, whichever comes first, right? So they are just bits of code that we're asking to run, and we're giving them a name. And so when we write our functions, right, and you know all this, but just to recap for anyone who wasn't here, when you write a new bit of function, you're writing a new bit of code that you can refer to by name. Now, that new bit of code might be a code that purely takes an action. Let's see. We could write a function called, let's steal some code from earlier in the evening. Write a function called both on, and it does two things. It does digital write. Let's see, what are my pins right up to? 9 on, digital write 10 on. What am I? Oh man, I don't know what I'm on. It turns both those pins on. I'm going to write a very similar function called both off. This is an arbitrary example, but just so we have a couple of functions, right, that are named both on and both off, and they turn a pair of pins on or off, right? That's a pretty, I'm not quite sure why you would need this function, but maybe you do. Maybe you have to turn both these pins on or off at the same time a lot, and so you encapsulated them in functions. In our loop function, we can use them like the Arduino's built-in functions. So let's write a little bit of code that doesn't use them. So we can say digital write 9 high, delay 500. There's that delay coming back again. Like I said, it's fast, it's easy, it's super useful, and our code's only going to do one thing, so I don't feel bad about using it. I'll do delay 500 there. So we'll flash the LED on pin 9. I'm going to have to set it up as an output. 9 output. I'm not declaring any of these as variables because I'm a bad person, but it's fine. Upload that code. So if I've written this right, we'll get the LED attached to pin 9 to flash on and off every half second. Great. No surprises there, right? So this digital write command here is itself a function. It's a bit of code that we're referring to by a name. It's a bit of code that's hidden from us. It's in a file that we, it's not showing to us in the IDE, but it's a bit of code somebody else wrote that says, hey, go in there and do whatever you have to do with the transistors to make the voltage on pin 9 be about 5 volts, and then make it be about 0 volts, depending on what this second parameter is. It's a bit of code that somebody else wrote that we wrote by name. In a similar way, we've seen functions that give us information back, like when we did int reading equals analog read pin, where's our pot? A5. We'll use our potentiometer for this. We'll make that an input. Well, I don't think I have to explicitly declare that. We'll upload that. Now, of course, I'm not doing anything with that reading, but that's all right. Right? So actually here, we can do print line reading. Oh, you can't see that. So I'm going to take that reading every second. I'm going to print it to the serial console just so we can see that reading going somewhere. This will all be this is a bit of setup, and then we'll get into more specifically what the return function does. So now once a second, I'm seeing that reading come off of the analog pin of my potentiometer, and as I turn it here, you can see we're seeing those analog readings on the serial console there, right? Again, all ground we've tread before, but all leading up to a point. So the point here is that there's sort of two ways of looking at these names, digital write and analog read. In some sense, this function went out and did things for us, and we didn't really obtain any information from us. Whereas this name, this function, this analog read, we were explicitly saying, hey, go out and do something and hand me a value back. I want to store the value of whatever this code is doing. I want to store it in a variable. I want to do something with it after the fact. And the way that you ask a bit of code to hand you a value back after it's run is using the return keyword. So these bits of code that we wrote a moment ago, the both on and both off functions, are kind of equivalent to this digital write function, in that they're code that we're asking to go out and do something, and we're not really asking for any information back on. They're just going to go out and do something. And the way that we sort of define a bit of code that says, hey, you just go do a thing, don't tell me about it, just do it, is with this void keyword. Void, meaning nothingness. It says, this is the position in a function definition. You say, hey, what do you want to get back from this function? If you say void, you're telling the code, hey, don't give me anything back. I'm not expecting any information. We're totally fine. If you put a variable type in that function definition, though, you are telling the IDE that you are expecting that this bit of code that you are writing is going to hand back a value to your code. So, for example, we could say int get value from pot might be our function here. And I'm going to move this bit of code that we wrote earlier into get value from pot. So int reading equals analog read 5, and then I'm going to return. I'm going to take this variable that, remember, we stuffed the value from analog read into this variable called reading, right? We're going to take that and return it. So when I reach out and say, hey, please run get value from pot, it's going to say sure. It's going to hand my code back an integer, and I'm going to tell it it's going to be whatever the value of reading is down here. So in my code up here, I'm now going to say my reading equals get value from pot, right? And now I can use this variable, my reading, in my serial.println command. And this will, let's see, I have to make this an integer. This will work exactly the same as I did a moment ago, right? So we get to this point in our code, we're going to say, hey, this variable I'm just declaring called my reading, I'm going to reach out and ask a bit of code called get value from pot to run. And it goes, okay, I'll run that code. It looks down and says, I've got a thing called get value from pot. I've got a new variable. I'm going to take some analog reading and stuff it into that variable. Now I'm going to hand back that variable, that value, that integer, to wherever I came from when I ran this bit of code. Where did I run that bit of code? I ran it up here. I'm going to take that value. I'm going to stuff it into my reading. And then I'm going to print it out in the serial console, and we can see what it is. Does that sort of roughly make sense? The return command is the command that when you're inside of a function, says, hey, this is the value I want to hand back from this function, if that sort of makes sense. Now, there's nothing to say that a function can only be one or the other of these sort of two types I've made up, of the go out and do things or hand me a value back function. They could certainly be both. For example, we could, this get value from pot function could also do additional things. It could turn pin 9, pin 10 could turn on. It could delay. It might be a bad idea for 500 milliseconds. It could turn pin 10 off and then take a reading. There's nothing that says that like there is no difference in the mind of the code between a function that does return something and a bit of code that doesn't return something. In our usage of them, they sometimes differ, right? And often, like I want to take some action or I want to sort of get a reading. Those things might be different, but you can certainly do them both at the same time. And especially like here's that example. So like I have been messing around with this week. Oh, I think I put it away. Well, you almost got tummy cam, but then you would know whether or not I'm wearing pants, and that just won't stand. So you get a little away cam. As I pull out a sensor module to make my point before I ask if there's any more questions for this evening, which I would welcome. But we'll see if I can't find this sensor, then it's all going to be, you will have missed tummy cam for nothing, and that will be a real shame. I also imagine that this all this rustling near the mic is sort of the opposite of ASMR, for which I also apologize. Oh, the sensor wasn't in the bin the whole time. It was in front of me. Well, that's a real shame. Hi. Sorry. The point I was going to make is what I have been messing with this week as a possible sensor for this thing is this ultrasonic distance sensor, which sends out a little pulse of very high frequency sound, and then oh, could you not hear me? Could you not? Oh, no. Oh, can you hear me here? Well, doesn't matter. I was saying witty things while you had that away music. I don't know if you could hear them. I hope so. They were very witty. Anyway, the point is I have this ultrasonic distance sensor, and the way that it works is you send one of its pins high to enable it, and then you wait a certain amount of time and get a reading back from it. So if I was going to write a bit of code that used this sensor, it would necessarily have to both write a pin high, then do some waiting, then do some reading. So in that sense, and then it would have to probably return that value to the code. So that code would have some output, would have some input, would have all that's here, but would also return a value to the code. And this return type that we would call it here, that determines what kind of thing we're returning back, can be any variable type. It could be an integer, it could be a long integer, it could be a Boolean. That's fairly common. In fact, we may have used that before, right? If you writing a Boolean function that says like, is house on fire? You might say if fire is yes, return true, else return false, or something, right? Returning, a function name that's like is something. Returning a Boolean is a pretty common thing. It's like just determine, whether this thing is true or false, and especially if you're going to have to determine in many points in your code if your house is on fire, or maybe the logic for whether a house is on fire is like so complex you don't want to like stick a whole bunch of code in the middle of some other code. Like, if temperature is more than this amount of degrees for this amount of time, and carbon monoxide, but smoke, but keypad, but mode, right? Wrapping all that up in a function that says like, hey, you go do all that logic and then tell me your conclusion. Is the house on fire? Return a Boolean, and your rest of your code could do something from that. So that is the gist of return. It's the command that hands a value back. It's also worth noting that that is the point that you exit a function. So for example, let's reverse this function here a little bit, right? So this is going to take a reading from the potentiometer, and then after the return function, I'm going to say, hey, turn on pin 10 for 500 milliseconds and then turn it off. This code, which I'll upload right now and show you, will never run, because when we get to this return keyword, we jump back from this code back to wherever we use that function, and we continue on from there, if that makes sense. So you'll see pin 9, our red pin here, is flashing. Pin 10, the yellow, it will never flash, because we will never get past this return statement in our function. So usually return will go either at the end of your code. You might have a couple of like if-else statements in here. They might each have a different kind of return. Like get value from pot maybe depends on like if we're in sensor mode, it returns the raw value. If we're in alarm mode, maybe it returns some scaled value. You might have two different return statements, different parts, but just know whenever you get to your return statement, you're immediately going to jump back from wherever you used it to the previous place where you called that function in your code. All right, cool. Yeah, good, super good question about like, and this is exactly the kind of question that I love, because like in these coding nights, we are slamming through a lot of stuff, and I'm doing it live, and I'm kind of throwing in things as I can sort of think that we haven't seen them before, but like obviously I'm me pair of eyes. I'm more interested in how these things hit you pair of eyes. So yeah, so thank you for asking it. Any stuff like that, you're like, hey, you use this term, this keyword, this structure that we actually, can we review that? Like, did we hit that again? Like that is super, super useful stuff to know. So thank you, Brian. That's super good. Always happy to like get, especially into like the nitty gritty stuff like that, because it turns out there's like a lot to know. Pay into like the making the Arduino smoke function. Yeah. Oh man, I should have saved. Lee and Travis sent me a picture earlier tonight. I don't have a great way of showing it at the moment, of an Arduino Uno box with a piece of masking tape across it that just said dead. Dead in like orange marker, question mark, dead question mark and that it's almost certainly in my handwriting. It probably dates to the haunted house that we built in fall 2011. I murdered a not insignificant number of Arduinos on that project, as I was learning on the job a little bit more about like the specifics of which kind of end channel FETs we should be using and which ones we could actually drive from an Arduino. Yeah, nothing like live entertainment to teach you a whole heck of a lot about expanding your possibilities. We blew up some FETs, if I seem to recall. We had a lot of success. That was a super, super cool project. But we also like murdered some equipment, and that was also really fun. Yeah, it's true. Kenneth makes a point, like, if you ever are in question, you should just throw away your dead Arduinos. I got bit by that last week, for those who were here. Just toss them, or put them in a bin marked Christmas tree ornaments and turn them into little Christmas ornaments and hang them on your tree. That's what I've been doing with the PCBs that are currently dead in my collection, is I make them into little Christmas ornaments that hang on afterward. Speaking of PCBs, because I see we're coming up on just about 90 minutes tonight. Came up to a real tight 90 as always, and I'm blowing out the candle now, for those who are worried about my house and home. Let's talk just briefly about what next week entails, and what I think we're going to talk about, which is kind of a fun topic, and will take, if you're interested in pursuing it, takes just a little bit of extra equipment, but it's aimed at cost savings in the long run. And here's what I think we should talk about. So the Arduino Uno, as we've sort of talked about back in the day, is a microcontroller, the chip itself that does the thinking, and a bunch of support components. You have a crystal that helps the thing sort of move at a regular time. We have some capacitors, which you talked about a couple weeks ago, like help provide little sips of power to the system when they're drawing extra power. We have a voltage regulator, which we've now talked about, right, which takes an external higher voltage and steps it down to the 5 volts we need to run. We have some connectors, we have some headers, we have the USB position where it plugs in, and a chip to sort of translate USB into the language that the code on the Arduino can speak. But that in a whole is what makes up the Arduino. The one step in moving from sort of fundamentals of Arduino into a more permanent thing is, let's say you have built something with an Arduino and you really like it, like it's working really well. And you'd like to make a more permanent version of what you have done. Because let's be honest, like this is well, I wouldn't say this is a good fire alarm. I actually might not even call this a fire alarm, maybe for legal reasons, but Let's say this was working really, really well, and I wanted to install this somewhere in my house to keep my family safe. Well, first off, I'd be a madman, but second of all, this is not a particularly stable structure, right? Breadboards are literally designed to be able to plug and unplug things easily. Night, Kenneth. The pin headers on an Arduino are meant to plug and unplug things easily. Like, everything about this is meant to be temporary. What if you want to make it more permanent? So next week, we are going to talk about taking the Arduino out of Arduino. How do you take literally this chip and transfer it to a more permanent form factor and the various strategies for doing that? Takes very little extra hardware, but it basically would take, if you want an additional chip. You could also pop the chip off of your physical Arduino, but you can also buy them for much cheaper. How do you turn a chip like this into a system that functions like this, but in a more permanent fashion? And what hardware and what strategies do you need to do it, and what can you do with something like that? The other possibilities that this opens up, right? This is as we talked about, I think back in week 1, an ATmega 328, which is a decently powerful chip. This chip costs about $2 on its own. Certainly much better than like the $15 that this costs, right? So already there's cost savings. But what if you don't even need, the full brunt and might of that expensive chip? You can get smaller chips. There's sort of 2 half-size chips in there, or you could go down even smaller. There's a little mini-sized chip there. There's an even smaller chip there. And if you wanted to go really small, you can go down to a little 8-pin chip there. And all of them now, thanks to the work of some really smart and clever people on the internet, can be programmed using the Arduino IDE. They're not drop-in replacements, right? Sometimes they have a little less memory, they operate a little slower, they might not be able to have all the interoperability and parameters, but like for blinking LEDs, for dimming things, for reading sensors, for taking in DMX, this is plenty. Not much more than plenty, but plenty. And these are like 40 cents a piece in unit quantity, which means like buying one at a time. If you buy 100 at a time, they're even cheaper than that. So I want to show you guys how you can get into, in a really, really simple way, using your Arduino and some wires, how you can program one of these to act like an Arduino. Because if you're going to be doing something permanent, taking a bit of board and soldering it on, and maybe even moving down to a smaller, lower power, slightly cheaper chip, is a really good way of taking something that's designed to be impermanent and making it into a permanent installation. So that'll be our focus next week. I'm stoked about it. I also I'm thinking through when I do this, I have a little bit extra hardware because I do this a lot. You really you can do the entire thing with just some wires and a breadboard. So don't be scared off by there's extra hardware components to it. This will be a pretty straightforward thing, and allows you to keep these cool projects around in chip form rather than having to lug an Arduino around in Arduino form. So that's next week. Miniaturized off-board Arduinos, taking them on the road. It'll be a great time. But with that, that's our 90 minutes for the night. This is again one of the longer ones, but thank you for hanging out with us on a Sunday night. As always, the code that we ended up writing for the fire alarm example, I will post on the website, not tonight, probably tomorrow, if you want to look through where we got. If you have questions, comments, issues, concerns, if you're trying it out, the easiest way to reach me, if you don't have any other way, is on Twitter at JeffersGlass. Email, there's comment form on the website. Next week's code and slides and examples will be on the website as well, jeff.glass/electronicsbash. Links to the slides will be there as well. Whew, what an evening. You're all great. Stay safe out there. Keep sending me pictures of what you're doing. I super love it. Keep sending me ideas and thoughts and yeah, it's really invigorating to see people take these ideas and run with them and play. Michael sent me a thing. He was like, I did this, but I did it with a shift register because we've learned about shift registers. We're going to try and do it with different buttons or different sensors. It's really cool. Michael says, can you post links to some of those chips? That's a great idea. Yes, I will post links to these chips at the very least in the on the website or on the Facebook event that we usually make for these, or in the video description for the scheduled stream. Where is best? Where is best to post information about what's coming up? Twitter's not really the thing for a lot of people, I think. I'll post it when I put up the Facebook event, and I'll have made the website by then. I'll post links to those chips in those 2 places, and possibly a couple other, like, yeah, some supplementary things. What's your favorite chip flavor? This is a good place to close. My wife and I, Mary, we are big fans of weird chips. We like to buy unusual chip flavors, and this week we are snacking on some chorizo and chipotle chips from Cermak Produce here in Chicago, imported from Mexico with the nutritional information stuck on the back with a sticker. And they're good. They're so good. That's all I got. Y'all are great. Stay safe out there. Stay healthy. Hydrate. And I will see you next week. Thanks, y'all.